All right, we'll start off with the syllabus today. Before we get that done, does anyone, they don't have any books yet that I can see. This is what the books in the bookstore looks like. It's a little thin edition. If you happen to have a thicker looking book like this, that will work too. This has both Physical Science 1 and 2 in it. This one is only Physical Science 2. Now be sure you pick up PHS112, not 111. They have both of them in the bookstore, so be sure you get 112. Okay? It starts with chapter 1 and goes through, not all of, but through chapter 8, I believe, or 9 it says. Wow. Okay. I don't remember seeing your name. Have you just added?
Nothing.
You have, okay. I have lost my pen. There it is. Oh yeah, there it is. Justin, right?
Yes, sir.
Okay. Good deal. Okay. All right. Anyone else come in since I called roll? Okay. Now, what we'll start with today is the syllabus, and that will take a little while to go through. Then we'll talk about the research paper requirement. There is a research paper due. Not a big deal, but just a little paper. And then I'll show you the locator card. I didn't get to update it, but I explained that. And then we'll talk safety. Got 3 safety issues we have to discuss. And then we'll maybe get started on, we will get started on the physical science. I don't think we'll finish chapter 1 today, certainly not in time to do a lab today, but most days we will have a lab. Now, on the days we have a test, what we'll do is have the test always, no matter what it's on, the last 30 minutes of the class. And if there is a lab, the 2 hours before that. If there isn't a test, the lab will be the last 2 hours of the class. And then whatever on the front end, that will be regular class. And that way, if you finish the lab early and we don't have a test, you can go, okay? If you finish the test early, okay, it's the last thing. When you finish it, you can go. You don't have to sit around and wait for everybody else to finish the test and then we start lecture or something like that. So I figure it's the way to get, if you finish early, you can go and not have to wait to start something else. So that's how we'll do. So today it's sort of like we have the lab part first, so that's not a lab, but it's just describing the course, and the class part will be at the end. But we're going to be flexible. It's not 2.5 hours of class and 2 hours of lab every day. If there's a test or something, those things get shifted around. I'll try to explain that as we get there. Any questions before we get started? All right. This is not this term's lab. Well, actually, they've taken out the dates, so I guess this could pass for this term's lab. Not, this is the part that's wrong. So yeah, I'll make the corrections, not make them, but I'll tell you about the corrections as we go. This is Physical Science 112, Physical Science 2. And if you do happen to have one of these books, you'll notice that Physical Science 2, the physics and chemistry portion is in the front of the book, and Physical Science 1, the Earth Science and Astronomy Earth Science part is in the back of the book. Because most other places, other than Alabama, Physical Science 1 is physics and chemistry, and Physical Science 2 is astronomy and earth science. Because you need to understand the physics before you can understand the other part. So when I teach the other part, I just have to leave off some of the physics part. So it's a little backwards, but it is the front part of the book. And what I was going to say, if someone is in dire straits of finding or being able to access a book, I do have one that one of my students, the last time I taught it, turned in and said, look, I don't need it. Anyone needs it, let them have it. So anyone desperately need a book, okay? All right, you win the prize, okay? And if you don't want it at the end, you can turn it back in and I'll give it to the next class, okay? Same true for any of you. I don't mind cheating the bookstore, okay? All right. So it is Physical Science 2, even though it's the front part of the book. Okay? It's a 4-credit-hour course. 3 of those credit hours are what they call theory hours. That's 2.5 hours of class. Then 1 credit hour for lab, so it's a 2-hour lab, okay? And it says 5 contact hours, but that's on a regular term course. On a mini term, it's almost 5 contact hours a day, twice a week. It's 4.5 actually, because they only do classes on 50-minute hours, so it turns out being that. Now, these times are wrong, but generally you'll get the idea. 3:15 to 5:45 is technically the class time, and 5:45 to 7:45 is the lab time. But again, we'll adjust those as necessary to do whatever makes the most sense. The class will always meet here. The lab will sometimes meet in 253, which is the closest lab to us right down the hall this way. 1 or 2 of the labs might go, one lab go across the hall from there, 252, and at least 1, maybe 2 of the labs will go down to 259. Now that's if there's no other classes in those rooms. The 252 and 3 are usually biology labs, so if they've got a class in there, we have to work around them. And the 259 is also used as a classroom, so if there's a class in there, we have to work around them as well. Okay? Everything's here on Bestman campus. Thursday, same as Tuesday. Everything's the same. My name is Charles Fowler. My office is A265. And for any of you, if you need to know where that is, we're right here in this corner classroom. Go out the door here, hang a left, go down the half flight of stairs, go almost to the end of the hall. Don't run into the wall, okay? Before you get to the end, there is a stairwell, okay? Don't go in the stairwell. The door right before the stairwell is my office. It's in between the mechanical room door and the stairwell. That's my office right there. Right across from the orientation classroom, if you remember where that is. A265. Okay. And we'll talk about office hours in just a minute. Now, on Fridays, I'm on the Birmingham West campus most Fridays. This Friday I'm not, because I'll be making up a trig class because I had a doctor's appointment this morning and missed my trig class, and they decided to let's meet on Friday and make up that class. So on Fridays, I'm in B122. That's in the academic building. That's the B building, 122. Are any of you familiar with the Birmingham campus? Not at all. Okay. Well, you are. Okay. Do you who are not familiar with, do you ever go there? So you don't care where it is. Is that right? Okay. For those who do know, you know, on the Birmingham West campus is sort of a circular drive. It's not a perfect circle, but a drive that goes around a set of 4 buildings, sort of in a rectangle. Okay, the building this way is the administration building. That's just offices and stuff. The long building on the back side, that's the B building, the academic building. The end of the building toward the gym, the tennis courts, and the baseball field, that's the end where 122 is, okay? If you come in that end, if you come in the doors at that end, you go down half a flight or up half a flight. Go up half a flight. When you get to the top step, immediately on your right is 122. Ask it, second.
Is there a library down there?
The library, okay. The back side is the B building. Then you have the C building, that's called the science building, and that's a real short building. And then the D building goes like this. That's where the library is. So the library's in front, sort of.
Oh, I'm thinking a computer lab or something.
Okay, yeah, there's a computer lab.
I've had 2 classes over there.
Right, okay. Yeah, yeah. Now the ACAT building is off. The new building is outside that. Yeah, you're talking about this. Yeah, there is a computer lab, a STEM lab, science, technology, engineering, math lab. There's actually 2 of them.
I had 2 other classes in that building.
Right. Okay. Well, yeah. Just ask anybody where Dr. Pruitt's office is. Everybody knows him, and I'm in the copy room of his office on Friday mornings. Usually only there 8 to 12. Not this Friday, though. My number here on this campus, 929-3449, and my email address is cfowler@austonstate.edu, which, by the way, most of the employees of the college, first initial, last name at austonstate.edu. There are a few exceptions. For instance, there's a Miss Cicely Martin down the hall here. There's lots of Martins, and there are at least one more that was first initial was a C. So she's C.M. Martin or something like that. There's a few that pick their own, like Mr. King, who teaches speech and English. He goes by Calvin King rather than K. King, Calvin King at AustinState.edu. But most of us is first initial last name. Okay? Now, on the Birmingham West Campus, this is the number in that room where I am. Okay. Now let me confess or warn you about something. I am so hopelessly behind in answering voicemails. I'm not even sure my voicemail works. It may be too full. I don't know. I haven't been able to access anything from it for a while. So if you're trying to call me on this number, if I don't answer, don't bother leaving a voicemail. I'm not sure I'll get it. Okay? So what I'm going to say is only call during my office hours, and I'll talk about those next. If I'm in class, I'm not going to hear the phone ring, and I probably won't get your message. Now, on this phone number on Fridays, don't leave a voicemail there either, because this is somebody else's number. There is a grant coordinator who uses that office Monday through Thursday, and she's not there on Friday, so I use the office on Friday. That's her phone and her voicemail, so if you leave a message, I can't even access it. She'll get it and not know what you're talking about, and probably won't be able to forward it to me anyway. So don't leave me a message really on either one, but definitely not this one. If you don't get me, if you're calling during office hours and you don't get me, just hang up, try it again a little bit later during office hours. Okay. All right, gotta scroll down a ways here. Yeah, there it goes. Okay. Oh, I was afraid it was going to do that. I wanted to leave these two up together. Okay. Now, these are not the correct office hours. I'll tell you the correct ones. Okay? No, I wanted to find this for my own purposes. Y'all are on block schedules over in the automotives, right? Do y'all still start at 8, or did y'all adjust the time? Okay. The rest of the campus went to 8:30 start times. So these hours are off a little bit for another reason, but that's one of the reasons. So no one pretty much except for y'all. You and some of your instructors are here at 7:45. So that's not correct. So office hours on Mondays and Wednesdays. Okay? On Mondays, I've got a 8:30 math intermediate algebra class followed by a calculus 2 class. Then I have a little break there from I should know my schedule by this time in the term, but it's when that class is over. I think, okay, 10 to 11:40. So from 11:45 until 12:15, I have about 30 minutes that I run back to the office and try to eat a little bit of lunch. Okay, I usually don't quite get to finish. So Mondays and Wednesdays, 11:45 till 12:15, and then I have a Cal 3 class that goes until close to 2 o'clock. So from 2 o'clock to 4 o'clock. That's the big chunk of office hours on Mondays and Wednesdays. Okay, little chunk there, 11:45 to 12:15, and I'm usually in the office before 8. And from 8 to 8:30 is also a time. I usually don't put them all down there because I don't have room to put them all. Okay? The biggest chunk is 2 to 4. 2 to 6 on Mondays. Okay, on Tuesday and Thursday, these times are wrong. It's basically 11:15 until 3:15 when this class starts. Okay, 11:15 to 3:15 on Tuesdays and Thursdays. Sometime in there, I'll try to eat lunch too. Don't worry, most of the time, I bring my lunch and I eat in my office, so you can come in anytime, 11:15 to 3:15. Okay? Then on Wednesdays, it's a lot like Mondays, except I have an additional physics class in the evening from 4:30 to 6:30, but it's over on the Birmingham East Campus, so therefore I have to leave here at 4. So basically on Wednesdays, it's at 11:45 to 12:15, early, half hour, and then there's 2 to 4, not 2 to 6. 2 to 6 on Mondays, 2 to 4 on this. So I got 4 hours, 4 hours, 4 hours, 2 hours. Then on Friday, it'll be 8 to 12 on the Birmingham campus, like I was saying, this room here. Okay, that's all I wanted to leave this up. Now, this Friday is an exception. Like I said, I'm going to be making up a trig class for the class I missed this morning, and we'll be meeting from 9 until 10:15 here in this classroom. So I'll be in my office between 8 and 9, and from 10:15 until 12 or so. Okay. Now, if I have to go to Birmingham, then I have to go to Birmingham either before or after, but I'll be here teaching the class. If I don't have to go, I don't like driving back and forth between campuses. I need to be in my office. So here's the course description. Pretty simple. Now, I didn't come up with this. No one here at the college did. This was done by a committee from the 2-year college system and the 4-year college system. The 4-year college and university, public college and university in the state of Alabama. And they decided this course provides a non-technical student, though y'all are pretty technical, with an introduction to the basic principles of chemistry and physics. Reverse the order of that. We can't change this. We do physics and then a little bit of chemistry. Physics and chemistry tie together pretty well. A laboratory is required, and we will be doing a lab just about every day. There may be a few classes we don't have a lab, but most of them will have a lab just about every day. Prerequisite, all it says is required by the program. What that means is if you have math at least through 098, you're going to be fine, okay? We will be solving problems, but they're going to be pretty simple. So if you can solve simple equations, that will be all that you need. No co-requisites, so don't worry about that. The text, like I said, is this one. Physical Science, Tillery is the author, Bill W. Tillery. Now that book that you have in the little thin one, it makes it look like I'm the author. I'm not. I'm just the one who chose the chapters. What they call that is a customized text, that they just pull out the chapters I'm going to be using, and that way you only have to pay for the chapters. You don't have to pay for the whole book if you're only going to use half of it, or less than half of it. So it makes it a little cheaper for y'all. Okay? So it's Tillery, Bill W. Tillery, Physical Science. This is the 11th edition. Now, if any of you have an older edition, I've taught, I can't remember what the first edition I taught from. It was way back, okay, probably 7th or 8th. Very little changes. Add a little color, maybe a few more exercises, or this, that, and the other. The Physical Science hasn't changed. A few things have been updated. You'll pick up on those. But mostly, if you have an older edition, perfectly fine. No reason to buy a new book if you have one of the older ones. Okay? It's a McGraw-Hill book. This one's 2017, which means it may have a shelf life of another year or so. They turn these over pretty quickly, and I'm sort of a cynic on this. The reason they turn them over and update you is that it's not that they put that much new stuff in them. Like I said, if you have one of the older books, it's about the same. It's that the book company only makes money selling new books. Once they've been out there a while and there's plenty of used books, they don't get anything out of the used books. So they make the authors do something to come up with a new edition every 3 or 4 years so they can sell more new books. Now that's my cynical view of it. I'm afraid I may be right. Students are expected to bring the book, paper, pencil, if you prefer ink, that's fine with me, to each class meeting. Calculators are permitted. In fact, I'll say encouraged. Okay. And here's Zachary. Anyone else come in and set Chicago? Okay. In fact, on tests, please bring your calculators. They're usually not too many. Now, the first test will have more calculations than any of the other tests. Okay, sorry about that, but they had such a terrible questions to choose from in the test bank. I had to modify some to make them closer to what we do in class. The rest of the chapters, they are mostly multiple choice with 1 or 2 maybe calculations or fill in the blanks. Okay? The first test, though, is going to have a few more calculations. So be sure you bring your calculator for that. And we will be working problems in class, most classes, so bring your calculators for that as well. A lot of the things you can do in your head or on paper, but it just makes it a little faster. Here's a paragraph they put on Blackboard, and they've updated a little bit, so it's a little more palatable, but it's also has some flaws in it. Now, they used to say, all students must use Blackboard to gain access to vital course information, blah, blah, blah. Then they changed it to courses. A course uses Blackboard, but a course doesn't gain access, okay? So they say we can't change it, and I apologize because it doesn't make a lot of sense, but you get the general idea. That you need to use Blackboard to gain access to vital course information, such as the syllabus. I know y'all are going to read the syllabus every day, aren't you? All right, good. Okay. Now, by the way, time out. Like I said, I didn't have a chance to do, I thought for sure I'd have to, well, I had a doctor's appointment this morning. It ran late, so I was late getting back to the campus, so that was part of the issue. Then we had a mini-term class that the instructor, her printout said it was one room, the student's printout said it was another room, and she couldn't find her room. And when we found it, there was a guy in a wheelchair that was assigned to that course, but there's no way for him to get up to this level. So we had to find a different room for him. So, and whenever something like that happens, even though this is humanities class, I'm the one that usually handles it on this campus because there's no administrator here that knows the campus. So anyway, I got tied up, doing that. So that shot, and I had to make out the calculus test too. And then I had the students coming by for tutoring and advising and stuff like this. So my day was shot, and I didn't get this updated. But I don't have the things on Blackboard yet. But hopefully before class next time, I'll have the syllabus up. I'll have it corrected. That's one reason I didn't put this one out there. And I'll have it on Blackboard. Now, most of the time, if I have a handout for you, I will hand it out. Okay, so I don't usually put those on Blackboard. The PowerPoint shows. They're not there yet, but they will be. Each chapter has the whole string of PowerPoints. They're not there yet, but they will be, hopefully by next time. Now, they're actually wind up being there in two ways. Number one, and by the way, let's talk about Blackboard for a minute. All of you are familiar with Blackboard, right? Okay. When you go to Blackboard, homepage for this course, there's a set of tabs over in the upper left corner. Now this set of tabs, it used to be about 2/3 of the page. Now you have to scroll down to see them all. They're just all over the place. Right here at the top, there's one that says instructor information or something like that. That's where I put the syllabus. Okay? No. Course information. That's where I put the syllabus. Then there's one for instructor information. That's where I put my locator card. When I'm in class, out of class, office hours, on campus, off campus, that kind of stuff. Which campus, that kind of stuff. I'll show you that in a few minutes, and I'll show you what that will look like. That's where that will be. And then further down the list, somewhere before you get and have to scroll down, there's a tab that says class handouts and more. Okay? If you click on that, that's where the research paper instructions will be. They're not there now. That's where the PowerPoint will be. But these will be in static form. They're just there. You can print them off. You can take notes on them. You can look at them. You can not do anything with them. You can do whatever you want to with them. That's one place they'll be. There under Blackboard, class handouts and more. Okay? The second place they'll be is down, continuing that thing till you get to the bottom, and there I'll have the link to the YouTube videos. Because I'll teach from the PowerPoints, so there they'll be, but then I'll be writing on them, I'll be talking about them, and you can hear me and see what's written. Anything that goes on the screen will be recorded. Now, my arm waving and this kind of stuff, that won't be on YouTube. That doesn't pick that up. Only what's projected on the board and everything that I say. Now, you see, I spend a lot of time talking to the board. My microphone's over here. I don't know how that comes across sound-wise. Later today, I'll be going to the back. I know that won't pick up very well, but I can't help it. I can't carry around the computer. The cord's not long enough. Okay, so anyway, the PowerPoint shows will be there in two forms. One under the PowerPoint listings in class handouts and more, or whatever that's called. And in that same folder in Blackboard, at the bottom, you'll find the YouTube videos, and the PowerPoints will be there again. That time, a bit more active. Activities. Most of the time, I'm not going to post much on activities because we're just going to be doing, I'll tell you every day what we're going to be doing next time. So you can get it there through YouTube videos. They'll be there. Occasionally, the school will post activities there. If so, check that. Okay. Assignments, I will put your research paper assignment out there. And then at the end of every chapter, I'll tell you things that's good to study for the test on that chapter. And we'll talk about what we'll do in labs, that kind of stuff. But it'll all be on the YouTube videos. Announcements, again, that's going to be mostly the school. If something comes up that I do have to, I hope this won't happen, cancel class or something like that, and I haven't had a chance to tell you in person in class, then I'll put those announcements there, but I'm hoping that won't happen. Now, that leads to this next one. I do not like this sentence at all, and when they modified it, they didn't change this. Failure to use Blackboard will severely damage your ability to pass the course. Have y'all ever found that to be the case in any of your courses? Frankly, I don't know. Maybe if a teacher teaches strictly from Blackboard, I've heard some of them do, yeah, it probably would, okay? But I don't do it that way. If I were writing this, I'd say the proper use of Blackboard could greatly enhance your ability to do well in the course. That's much more positive and closer to reality, I think. I do not like this sentence either. Students should always check the Blackboard announcement page and task pages, whatever they are, prior to coming to class. Why would you need to do that? Only one reason I can think of, maybe there's others, comma, in case the instructor has canceled class.
Or you missed a class.
Huh?
Or a student missed a class.
Yeah, well, yeah, but it says prior to coming to class, so obviously they're going to come. So, guess what, team? I'm going to try never to miss a class, okay? Some of you have been in my class before. How many did I miss? None. And I'll try always. I'm going to try to be here. Now, if something comes up that's an emergency, I probably am not going to have a chance to get on Blackboard. Oh, excuse me, before I go in the ambulance, let me send the Blackboard message. You know, not that. But usually, I hope that's not going to happen either. But generally, this late in the day, I'm going to be here. Okay? So it won't be travel or something like that. Now, here are what they call the professional competencies and the objectives of the course. This is such a pain. Okay. Course student learning outcomes. Students will describe the nature of science. This is sort of a blah, blah, blah one. Identifying, quantifying properties, use measurement systems, calculate densities, identify laws, principles, models, and theories. What is that stating? That's stating chapter 1. Okay? That means we're going to do chapter 1. And if you go to chapter 1, you'll see all those things are listed there. Students will solve problems using the basic principles of motion. That's chapter 2. Students will solve problems using the basic principles of energy. Chapter 3. Students will solve problems using the basic principles of heat and temperature. Chapter 4. Students will solve problems using the basic principles of electricity and magnetism. That's chapter 6. Chapter 5 is sound, waves and sound, and I found out we just don't have time to do everything. I figured electricity is more important for, especially the automotive folks, than probably waves and sound. So I put that one in. And we do have to do something in chemistry, so students will solve problems using basic principles of chemistry. That's chapter 8. I can't remember what 7 is, but we skipped 7 as well. Okay? Your little books like that, the chapters we skipped, they're not even in there. They do have chapter 9 in there, I noticed, so evidently they put one more in case we finish everything in 8 and have time to do a little bit in 9. Okay? But students will write a library or internet-based research paper. And again, I'll talk about that a little bit later. Not a big deal, but it is a deal, okay? Now, these things, and students will conduct laboratory experiments and write the results. Most of the time, I'll give you the forms, you just fill in, okay? It's nothing you have to write like in a lab manual or something like that. I'll pass out those lab instructions. Now the book, there is a lab manual that we used to order with it, but then I made copies because people were having to rip those apart and stuff like this, and they wanted to sell them back, so I made copies of it. So why make you buy a lab manual if I'm making all the copies anyway? So those that come from that are usually going to be thick, okay? Pages, you know. Those that I've come up with, I didn't like the ones in the lab manual. They're much thinner, much shorter, okay? They still have about the same amount of work to do. You just don't have to write up as much, okay? You'll see the difference. So chapter 1, we'll do one lab assignment. Now, this is so bizarre. It's probably the longest and most involved lab that we do, okay? On the shortest chapter, one lab assignment, and it'll take just about the full 2 hours, okay? Most of the labs don't take the full 2 hours, but that one, a lot of times does. And sometimes we have to come back and do some the next day just because it's so long, okay? There'll also be a test at the end of chapter 1. And that test will be the only more quantifiable test, you know, more problems to solve and stuff like that. So chapter 1's a little bizarre because it covers sort of nebulous stuff and a whole range of stuff. So the questions they had in the test bank were pretty pathetic. Okay, chapter 2, when we talk about motion, that's a big, long chapter, okay? So we'll break that into, I think, 3 labs, okay? So that's why it's lab assignments, not assignments. So, and then, but one test at the end. Chapter 3, principles of energy. Again, I think that's 3 labs there too. So 3 lab assignments and the test. Chapter 4, heat and temperature. That's either 2 or 3 labs and the test. And basic principles of electricity and magnetism. Again, that's at least 3 labs and the test. And chapter 8, the chemistry chapter is just 1 lab and then the test on that. Then you have the research paper that measures this and the comprehensive final exam. Now that sounds pretty hairy, doesn't it? Actually, you'll probably find this is about the easiest test that you'll have over, okay? The others aren't going to be hard, but that's going to be pretty easy. But it will be comprehensive. It will cover the high points of everything else we cover. All right, any questions on what we're going to do? Okay.
I have a question. So,
Yeah.
Is it true, so even though we're not going to do chapter 5 and 7, we just going to do chapter 1, 2, 3, 4, 6, and 8?
Right. Okay.
Instead of...
Yeah. And if you have the little books, those are the only chapters in there, except I think they threw chapter 9 in, which we've never gotten to yet. But unlike, well, remember in the Physical Science 1, we skipped chapters 21 and 22. Yeah, we just didn't have time to do all those. Same thing here, we'll skip chapter 7 and chapter 5 and chapter 7. Okay. Now, let's get to how are you going to be graded, evaluated, that kind of stuff. Let's see if we, whoa, a bit too far. All right. They have this sentence in there that I think is redundant. Following this is the breakdown of how each student will be evaluated, blah, blah, blah. Research paper is required. Notice that's not recommended, optional, or anything else. It's required. It can't be dropped, okay? You will get a score for the research paper. You don't turn one in, a big fat goose egg, okay? Don't want that to happen, okay? It will count as a test, and it cannot be dropped. Now, chapter tests will be given at the end of each chapter. Remember, there's 6 chapters, that's 6 tests. The lowest chapter test score may be dropped. If it helps your average, I'll drop your lowest test score. Now, you might say, well, that always help your average? Well, not if you didn't turn in a research paper. That's a 0. You're going to need every test score you can to bring that up. So turn in the research paper so you can, I can drop your lowest test score. There will be at least 1 laboratory assignment for each chapter covered. Chapters 2, 3, 4, and 6 will have multiple, either 2 or 3, most of them 3. The lowest lab assignment may be dropped if that helps your score. Okay? A laboratory grade will be averaged from the remaining laboratory assignments. And here's how I do this. Remember, 4 credit hour course, 3 on theory, 1 credit hour lab, even though it's 2 hours, right? So that's 4 credit hours, 1 for lab, 3 for, so I count the lab as a quarter of your grade, 1/4 of your grade. So that's why it's 25%. And to make it easier on me, I make every lab worth 25 points, not 100 points. Your tests are going to be worth 100 points, the labs are going to be worth 25. So you make so many points out of 25. That's what your score will be on your labs. So at the end, I just average up. If I drop the lowest lab grade, average them together, that gives me a number between 0 and 25, hopefully closer to 25. And do the average of your paper that can't be dropped, the remaining test scores, probably 5 of them, except for the one I dropped. The comprehensive final exam cannot be dropped either, so that's usually going to be a pretty good score. That will count as 25%. That average will be 25%. So what I get from that, based on 100, I'll take 75% of that, add it to your lab average, and your final test. I mean, your final grade comes that way. The comprehensive final cannot be dropped. So at the end of the term, everybody takes that. But like I said, it's usually a pretty easy test for most people, and people usually do pretty well. Okay? Now, they put in all this stuff about plagiarism. I hope you've heard about it in other classes, so just don't even do it. Okay? Students will be graded normal, 90s are A's, 80s are B's, 70s are C's. Stay there. Don't go below this. 60s are D's, anything below that are F's. Okay? So, and you do know at Lawson that A, B's, and C's are the only passing grades. F is the only failing grade, but D is in no man's land. If you make a D in a course, you have to retake it. Okay? Even though it's not failing, it's not passing. Okay? It's rather strange. And one reason for that, no one transfers D's. We don't transfer D's in, and schools don't accept D's when you transfer out. So that's why it's counted as sort of no man's land. F is a failure. Okay, now a D is not as bad as an F because you do get 1 quality point for a D, you get 0 for an F. You get 2 for C's, 3 for B's, and 4 for A's. That's how you get a grade point average. Okay. Now, I think I know who put this in. I don't know for certain, but I believe I do know. And the person was not a math person. And this next sentence didn't make any sense before, and I tried to make it make more sense. I didn't get this one correct. Here's what this person put. The instructor rounds grades upwards. Now that's not totally true. In the student's favor, okay? Never downwards. So then look at their example. For example, a 79.5 would be rounded up to an 80%, of course. But a 79.4 would remain a C. In other words, it's rounded down to a 79. So why say never downward? So this doesn't make any sense. The way I'm going to correct this. I round normally. Anything that's a 0.5 or higher, you go up. A 0.4 or below, you just drop. Okay? It's a normal rounding. Okay? But I'm dropping your lowest test score, dropping your lowest lab score, and that way I'm elevating. So that's how things are in the student's favor. Okay, attendance. All right? You're expected to be here, especially on a mini-term class. Every class meeting is equivalent to a week of class in a regular course. Okay, because it's normal courses are 16 weeks. We're 8 weeks. So every class in here is equivalent to 1 week in a regular term class. Now, you guys do everything except for summers on mini terms. So everything is 8-week courses for you. So you're used to it. But we cover a lot of material, and so missing a class is going to really hurt. Now, I do record it. You can go to YouTube videos and see and hear everything we've done in class, but you can't ask a YouTube video a question. I mean, it just doesn't ever answer. So please try to be here, okay? So this is a lot of blah, blah, blah. Read it. You know, it is good stuff. And the main thing is, I'll try to highlight this. Go to the YouTube video, get as much as you can. If we've had a lab that day, now this is where it really hurts. And we are going to have labs most days. If you miss a lab, it's really hard to make up that lab. I'll do everything I can to help. You know, I've got 4-hour blocks here and there during the week. I'll be able to do it. But you're probably going to be in classes most of those 4-hour blocks. So therefore, it's going to be really difficult. So if you do miss a lab, see if you can get a buddy or somebody to either get a copy of that lab for you and collect the data, but you do the work in it, if there are questions answered and stuff like that, because that's not often, but some of the lab stuff does show up on tests. Those people that were just in the Physical Science 111, you know that a few of those things did occasionally show up on the test. Okay? So anyway, I'll let you read this. Now here's the thing about withdrawals. Now this will apply to most of the folks on this side more than that side. I know we got a couple of automotive students over here. We may have some non-automotive students over there, but whatever. Remember, D's and F's you have to repeat. Okay? An F is always going to hurt your grade point average. 0 points. I hope a D will hurt your grade point average too. A 1.0 is not going to help many people's grade point average. Okay? So if you suspect or feel like, and this shouldn't happen in this course, if you come to class, do the lab, it shouldn't happen. But if you get hopelessly far behind and it looks like there's no way that you can pull out anything above a D or F, you know, then I think it's far better to withdraw. Because a W does not hurt your grade point average at all. Now it can affect your program if you might have to come back an extra term and catch up the course, but you can do that, most of you, I think, okay? But a D or an F, you're going to have to come back and make up the course, and it hurts your grade point average. A W, you're going to have to make up the course, but it doesn't hurt your grade point average. Now, if you're on financial aid, most of the time they'll pay for you to retake the course once. They won't repay for you to take it twice. But you make a D or an F, you're going to have to retake it anyway. A W is no different from that, except it doesn't hurt your grade point average. So I can't see any reason if it looks like you have no way other than making a D or an F, I can't see any reason not to take a W instead. Okay? Even if you're going to have to pay for it, you're going to have to pay for it with a D or an F. You know? So whatever. Now, check with your advisor. You know, do everything it says there. But frankly, that's my advice to just about everybody. Now, makeup work. Okay? Somebody else put all this stuff in here. I certainly will, if you have to be out and you need to make up a test, yeah, you can make up a test. Okay? There's no problem with that. You have to come in during office hours, my office hours, to do so, but the tests are not that hard. In fact, most of the tests I allow you 30 minutes to finish, and most people finish them before that. So they're not all that onerous, so you certainly will be able to come back. The labs, that's the tough part. That's why I say get with a buddy if you know you're going to be missing, and get the data from them so you can make up that test. Okay? Lateness policy, try to be here on time. Y'all were here early, most of you. I know some people, I've had other students in classes that are on, have classes on the Birmingham campus, and they only have 15 minutes to get between the two, and it usually takes me close to 30 to make that transit part and that kind of stuff. So I understand if you have to be late. Some people are working and that kind of stuff. Okay? Now, this academic integrity. They go on and on and on, and it's important stuff. Don't plagiarize. Don't cheat. You know the drill. Okay? I'm not going to read this to you. You can certainly read it yourself. Okay? And then personal decorum. Yeah, some of the stuff they say in here is it's just common sense type stuff. Okay? But here's one right here, eating or drinking. You know, y'all probably been in class since 8 o'clock this morning with some little breaks in between. Do you have much of a break in between your blocks? That takes 15 minutes between the last one and this one. So if you need some Gatorade or something like that to get through, I'd rather you have that than you passing out or something in the class. So, yeah. So you know this stuff. It's all over the place. Now, course concerns. All right. This is if you have a gripe about the way you feel like the class is going or has been taught or something. If you have a gripe or a complaint or concern, they outline what you need to do. First, check with the instructor. That's me. Okay. We'll try to do it. If you have some problem, let me know. You know, we'll be asking you, how's the pace going? Is this okay? Yeah. Okay, so let me know. Second, go to the department chair. Let's see. That would be me. So I am a department chair. But we have another one too. Dr. Tracy Wilson is also, she's natural science department chair. I'm the math department chair, but we work together. You can go to her if you need to. And then, if that's not, then you can go up to the chain of command. The associate dean is Dr. Carl Pruitt, whose office I'm in on Friday mornings. The dean is Dr. Sheree Davis. The vice president is Dr. Bruce Crawford. I'll help you write me up if you need me to, okay? But let's try to resolve things. Don't just get angry about things and not let anyone know, okay? Now, they give the Lawson State website. You can find all this information about this kind of stuff there. Let's get the student. Ooh. Okay, I don't know why it did that. Okay. Yuck. So aggravating. All right, here it is. Student statement on discrimination and harassment. Let me summarize this. We don't tolerate it. We don't condone it. If we find out it's happening, we deal with it. We deal with it quickly, fairly, but we don't want it happening here. Now, what I count here is also is bullying. And so far I haven't seen much, but I know it happens in the rest of the world, okay? We don't want it happening here. So we don't want any kind of discrimination, any kind of harassment, any kind of bullying. It just will not be tolerated. So if you see or even sense that someone's being picked on, discriminated against, harassed, let me know, because we don't want it happening here. Most of the time, no one's going to do it in front of me. And I've been here 21, 22 years, something like that now. I haven't seen any, okay, anything much that could. I've heard a few things, okay, but I haven't seen any. But that's because they're not going to do it in front of me. But you might see or hear or sense it. Let us know so we can keep it from happening. Now, one of the things, this isn't discrimination or harassment, but it'll give you just an idea. It was one of the first few years that I taught here. And back then we had an automotive math curriculum because we were at Pastor State Technical College then. So everything was geared for the technical programs. We didn't have transfer students to four-year schools. When we became a community college, Lawson State, then we did pick up those. But at that time, so we had automotive math, okay? I was teaching automotive math back then, and there was this one young kid just out of high school, and you can tell he was there just because Daddy said, you got to go to college, you know? Well, what do you want to make? I don't know. How about automotive? Okay, yeah, okay, well, yeah. Sounds easy to me, you know. He didn't do well in his automotive class either. So he was just sort of becoming an astronaut, taking up space. No, I'm sorry. It was just here. And he wasn't really here in many ways. And one day at lunch, I didn't see this, but I heard about it. I noticed he usually was here in class, so he didn't do much. Well, he started missing a few days. And finally I said, well, where is whatever his name was? And they said, oh, you didn't hear. And this is what the other students told me. One day at lunch, he just decided to start walking across people's cars in the parking lot. Okay. Someone saw him, yanked him down from there, took him to the dean's office. In a few minutes, he was off campus, never to be seen again. Okay. Now that's not discrimination or harassment. In some ways, harassing the cars, I don't know, but disrespecting other people's property, he was out of here, okay? And that was what it took. He was treated fairly, he was given but that just wasn't, and that's what we feel about discrimination and harassment. We don't want it happening here. All right, Americans with Disability Act. As I've already said, I'm hard of hearing, so I sort of identify with people with disabilities. We had like I said, today when I was hoping to be working on something else, we had a class assigned to a room up here on the second floor. A guy who signed up for that class who was in a wheelchair. There's no elevators in this building. There's some old, ancient lifts in two of the stairwells, and those parts are almost impossible to find. They're that old, so that neither one of those are working. So we have to move classes down to an accessible floor. And that's what I spent a fair amount of time with. We try to deal with whatever it takes to give people the opportunity to learn without whatever the disabilities they may have, we try to accommodate. Okay. Now that will include things like hearing, vision, dyslexia. I had one student probably 3 or 4 years ago who had pretty severe cerebral palsy, okay? He was not able to take notes. He didn't have that good a hand control. He was confined to a wheelchair. We moved down to a lower level so he could attend the class. So we did whatever it took. He had a note taker. The school provided a note taker for him. In fact, the school advertised to students, if you're able to take notes from somebody, there was a need. I think it was over on the Birmingham campus. So we do whatever it takes to try to make sure everybody has a chance to learn and to do well, okay? So you can read through this. If you have any questions, Dr. Renee Herndon is here on this campus. She's in charge of Office of Disability Services. That's the number on this campus, on the Bessemer campus. Mrs. Janine McCoy Jones is on the Birmingham West campus, in the Space Center, I believe it is. So you can contact either one of those. You can go to the college website, request a meeting online. There's lots of ways you can access the disability issues. Okay. I don't think there was anything in that. Yeah. Okay. Here's the college calendar. This obviously is not this calendar. This is last January. I'll put in the one for now. You can find this on the Lawson State webpage under academic calendar. But I'll put it on here just like you see here. Okay? Days will be different, of course. Okay? And then finally, there will be a student acknowledgement form. It's not out there yet because I don't have the syllabus updated. When I get it updated, put it on Blackboard, and you can take this form. You can either print this last page, sign it, and bring it to me, or you can pull it off here, type your name in, and email it to me. Whichever you want to do, but this is what you do at the end. Are there any questions about the syllabus now? A lot of blah, 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 right? Okay. All right, so there's the syllabus. If there are no questions, I'm going to go on and close that out. All right, let's now talk about the research paper. Again, I try not to make this an onerous thing, but you see SACS, which is our accrediting agency, Southern Association of Colleges and Schools, they're coming within the next year or two. There are some preliminary visits going to be very soon, and then the main visit will be another year or two out, but we're right on it. Periodically, they ask for samples of student writing, so that's why I ask students to write something up. Okay, that's one reason. That's not the only reason. What you need to do is choose a topic within the scope of this course. Physical science, physics, chemistry, okay? There's lots of options there. It could be a person. We're talking about several people. Every chapter in the book has at least one person they highlight, but there's several other people being addressed in that chapter. You'll hear the names over and over. If you want to write about a person, that's fine. A theory, that's perfectly fine. A phenomenon, okay, something that happens in nature. The folks who were in the Physical Science 1 at least one person I think wrote on the Big Bang Theory, okay? That's a theory. It's physical science, okay? That was perfectly fine. And application, I really like application papers, something that someone is interested in. I had a guy, decades ago, in a trig class, sat right back in the seat you're in right now, in this classroom, and he was a forestry major. He was taking most of his classes at Jeff State, but he was having a hard time with math there, and he drove by here every day, so he decided to come in here and try math here. And he wasn't a great math student, but he was okay, and he passed here, and he liked it. But he wrote his paper on the use of trigonometry in estimating lumber. When a forester goes out to buy a tract of lumber, he doesn't climb the tree and measure how tall it is. He uses a trick to determine the height of the trees, okay? Great. I mean, it was a good concept. An application made sense to him. In regard to most of you guys, I've had papers, I can't think of them all. I remember one guy wrote on the physics of the Wankel engine. Does anyone remember the Wankel engine? The Mazda, rotary engine. Wrote on the physics of that. Not a great paper, but it was a good topic because it was something he was interested in. I think I've had at least one or more papers on anti-lock braking system, the physics of that. Or you just, I can't think of all the terminology, but something to do with regenerative braking. I remember that was a really good topic, I thought. Okay? So you can pick something that you're interested in. That's what I want to see. But related to physics and or chemistry. Okay? I noticed that a few years ago, probably close to a decade ago, we had a program here in the automotive on alternative fuels. They don't have that anymore, do they? But somebody could have written more of a chemistry type paper written on that, based on that. So anyway, there's plenty of opportunities, any application, or any other such topic about which you might have an interest. I really want to see those. But if you just want to write about a person, that's fine too, or a theory or phenomenon. Now, I also have, in recent years, expanded this to include internet applications or demonstrations. What do I mean by that? Well, let's say there's a concept that we're talking about in here. Okay? And I'm just going to pick a simple one that I don't think anyone would have an issue with. But let's say in electricity and magnetism, something on the Van de Graaff generator. I don't think we're going to talk about that, but I have had a paper on that before. And what it was, they didn't understand what the book said about it. And what I said about it didn't seem to increase their understanding. So they went out and found a YouTube video or something like that on it and said, oh, that's what they're talking about. So he wrote his paper, he or she, I can't remember which it was, on that application and how it was improving his or her learning and understanding of what the concept was. So if you find any kind of internet application or demonstration, you want to write on that, how it helped you understand the processes or things better, maybe something to do with thermodynamics or something like that, anything such as that, you can write on that as well. Okay? So what I'd like you to do either today or Thursday, is write your name on a piece of paper. That's pretty hard, isn't it? Okay? And then also the topic, at least now, that you're thinking of writing on. Okay? That's why I say you can wait till Thursday so you can sort of skim through the book, see what is going to be covered, think of things that you'd like to investigate, and write that topic. You can always change your mind, but I want to get you thinking about it now because we only have 8 weeks. And that 8 weeks is going to fly by faster than you can imagine. Okay? So do that. Now, there's a piece of paper with just your name and a paper topic on it. If you want to write something else on that piece of paper, but this is not required, it has nothing to do with the course. But it sometimes is a necessary thing. Periodically, I'll have a panic knock on the door, and an administrator will come in and say, do you have a good number for blah, blah, blah student? Because we have somebody's calling trying to get in touch with them desperately, and the number in the system is not going through. Do you have a number for that? And if I have that number on a piece of paper, I say, yeah, here it is. I'm not going to give this to another student or anybody else. It'll only be within the college itself. But there are times when maybe your cell phone died, and that's the only number the person has, and they're desperately trying to get in touch with you, or anything else. So if you want to write down on a piece of paper, or maybe you didn't have the cell phone when you applied to the college, so the number that's on there isn't any good, okay? Or someone, when they were transposing, or when they were typing in the number, switched 2 digits by mistake. So the number they try to get, no one can get, that's not going through to you. So if you want to write down your very best phone number, you can do that. You don't have to if you don't want to, but you can do it if you do want to. Now, if that is a cell phone, which I bet you it's going to be for most of you, there is a chance that battery could die. You can leave it at home, leave it in the car, or get run over by a truck, or anything could happen. You drop it, step on it, or anything could happen. If you have a good backup number, Mama's landline or whatever, if you want to give me that one, you can. You don't have to, but if there is a good one. Now, no, just from past experience, I bet you a bunch of you work just about every chance you get when you're not at school. I figured, okay? So if a lot of jobs don't want you talking on your cell phone, and Mama might not be able to reach you, okay, especially if she's not home. If you can take emergency calls at work, if you want to give me your work number, you can do that. I don't need any of those, but if you want to give me 1, 2, or 3 numbers, you can do so. Since you got a piece of paper there anyway. When the course is over and you're no longer in my class, they get shredded. They're not going to be out there anywhere else. Okay? So, I do need your name and your research topic. If you want to write the phone numbers, you can. Now, you'll need to find at least one, but 2 or more are better, outside sources for your paper. Now remember I said every chapter usually features some scientist or somebody. For instance, this chapter I happen to open here in Energy features James Prescott Joule. It has a great little blurb on him. That can't be the source of your paper, okay? This can be the source of the idea for the paper, but it can't be the source for the paper. You need to get something outside the book. That's the main reason I make the assignment. Yeah, SACS wants this kind of stuff, but I want to get you out of the book into the real world, so to speak, so you see how this stuff is applied, okay? So therefore, it needs to be something outside the book, okay? It can be books, journals, articles, other such materials you can find in the library, either this library or any library. Here's a squeaky one, or any legitimate source found on the internet. There's 2 problems with that, okay? Now, let me start with this. During my lifetime, and it's been pretty long so far, I can't think of anything more impressive that's been developed during my lifetime than the internet. I don't think there was any internet around in 1951, not that I know of anyway, and so the whole thing has come about in my lifetime, and it's incredible. It's absolutely amazing. There's 2 big problems with it, though. At least 2. There may be many more. One, at least, and I think way more than half the stuff on it, is total garbage, okay? It's just worthless, not even worth looking at or listening to or anything else. The other issue is sometimes you don't know which half, okay? So you have to be very, very careful with the internet. So if you have any doubt about your source on the internet, run it by me. I'll look at it and say, I've never heard of this person. This doesn't seem to be well documented. I'd be a little shaky, concerned about using that. Try something else, But I could look at it, this is backed up. I've seen many other things about it. Yeah, that's okay to use. So you can probably do the same thing. The textbook is not an outside source. Great material in here, but that's not a source for your paper. You cannot get outside the book. Okay? Now your paper must be at least 1 word processed page of text. Notice that, not handwritten. I don't even want it typed. I want it word processed. Okay? Now, what do I mean by a page of text? I don't know if it's your English classes or what, and it's fine with me. I don't have anything against it. Usually there's some header at the top, and then you skip a few lines. You have the title, you triple space again, you start typing somewhere about here. What's one page of text? It's going to go to the bottom of this piece of paper, and then on a separate piece of paper, going to come down until it passes that point. That's a page of text, not something that you expand your margins and stuff and have just a few words in the middle of a page. That's not a page of text. So you get the general idea. It's going to be at least 2 pieces of paper. Okay. Now, I do want it double spaced. Not that I'm suggesting I want it double spaced. This is single spaced. So you see, a page of text is not that much double spaced. Okay. So double spaced, 12 pitch or 12-point font. I don't want any 26-point font that 3 words fill up a page and you say I'm through. That's not going to work, you know, so don't even try it. 12 pitch or 12 point. I don't want the tiny stuff that it's hard to read, but I don't want the big stuff that you're just taking up space. I don't care what font you use as long as I can use it. Okay, I read it, okay? I don't read hieroglyphics. I don't read Old English, and don't get fancy with it, anything like that. Keep it simple. Times New Roman is just about all the word processing defaults. This happens to be an Arial. I just like Arial. Courier is fine. There's just tons of good readable fonts out there. Pick any one of them. I don't care. Try to keep the paper less than 2 pages. So shoot for between 1 and 2 pages of text. Now, I don't take off points if it's too long. I do take off points if it's too short. And I do hold it up to the light and make sure that it covers at least 1 page of text. Okay? Now, I say I don't take off for it being too long, but this hasn't happened often, but it has happened a few times. Now, I've been, like I said, teaching here for something like 22 years. I didn't do it the first few years, but let's say at least 18 to 19 years I've required papers. I've had anywhere from 5 to 8 classes a term. Not all of them have been this big, but this is a little above average, but lots of students. In every class I teach, except there's one physics class I don't do this in, but in developmental math I didn't, but most of the classes I do. So I've seen a lot of papers, okay? And I've only seen this 2 or 3 times. Someone just decides, well, I can't do a quality paper, so I'm going to baffle them with quantity. In the Navy, we had an expression for that I won't say out loud, but if you can't dazzle them with brilliance, you baffle them with BS, So I don't want that, so don't even try it. But this person or two that have done this in the past just tried to impress me with how long they could make the paper. But it was a lousy paper. They were very careless. They didn't do a good job. That's probably why they made it long. Well, guess what, team? That doesn't help you any, okay? Here's why. When you turn in the paper, it's a 100-point paper. Then I start reading it. I can hear you now saying, don't read it. No, but I am. I will read every paper that you turn in and read it carefully. And as I read it, if I find errors, you start losing points, okay? So if you turn in a long, poorly written, poorly proofed, lousy paper, the longer it is, the more I read, the more points I'm taking off. That actually hurts you. A good paper, whether it's 1 to 2 pages or 3 or 4 pages, you're not going to lose that many points. So if you get so excited about your subject, and I've had people who do this, I didn't know where to stop. I have a feeling most of you won't have that problem, but if you do, go on. As long as you give me a good paper, I don't mind if it's more than 2 pages. The reason I say 1 to 2 pages, so it won't be so onerous. It won't be so hard for you to do. I want it to be something that you benefit from, but it's not too bad. Okay? So, now, what format to use? I don't care. The English department usually teaches MLA, Modern Language Association format. If that's what you're used to and that's what you got, go for it. It's perfectly fine. A lot of the science type areas use a format called APA, American Psychological Association. They came out with this great format early on. People looked at it and said, I can't think of anything to do to improve this. Well, let's just use theirs. So a lot of people use APA. But there's tons out there. I'm a member of about 3 or 4 professional societies, and I think every one of them has a different format. So any format will do, but the main thing is for you to be consistent with the format. For instance, it's just a simple thing. If you start blocking paragraphs, block all your paragraphs. I've had people, they'll block this page, on page 2 they start indenting, and I don't know why, or vice versa, you know. If you do one, stick with it, okay? Now here's one that I don't see often, but I do see it occasionally. Let's say they have 2 or 3 sources, okay? And up here they reference the first source. So they put a parentheses and put the author's name, comma, year of publication. Close it out. And down here they reference the same type of an article, but it's a different article. And they open parentheses and type the name of the article, comma, page number. That's not consistent. I think I know what happened. This source used one format, so they copied the format that source used. This source down here used a different format, so they did the format that source. No, that's not what you do. You choose your format, and then you do the format according to that, you know, not according to what your reference is using, okay? So be consistent, that's the main thing. Now I know that books have different formats from journal articles. I understand that. These were the same type of thing. Okay. Okay, spelling, grammar, sentence structure, all those things that in the English class are going to lose you points, they'll lose you points here too. Maybe not as many. You know, I'm not real anal or retentive about those, but if it's an error, it's an error, okay? So guess what? Just about every word processing package out there has spell check these days. Use it! I get papers coming in I know did not use spell check because there's no word in the world that spelled like that, you know. They didn't use it. Grammar check. Just about all of them used to have grammar check on them. Use it, okay? I've had some sentences come across that I can't figure out what they're saying in it. And I know a grammar check would say awkward sentence, or, you know, they have some sort of suggestion for you. I can tell it wasn't used. And of course, use good proofreading, okay? Now, let me just give you a couple of examples of that. I know this is taking too long, but my high school English, I think my senior English teacher, when she assigned us a research paper, here's one of the things I still remember her saying. She said, get your paper done early, which I'm trying to get y'all to do here too. Get it done early and set it aside, and she used the term, let it rest, okay? Just set it aside for a few days, over a weekend, something like that. And then pick it up later, and here's the other term she used, with fresh eyes, and read it. And if you run across something that you say, what did I mean by that? Wait, what does that say? That's what the reader is going to be saying too. And here's what happens, because I've had it happen to me many times. As you're typing along, you know exactly what you want that sentence to say. And for you, it's saying that. But when you go back and read it later, it's not quite getting that point across. You may have left out a word. You may have typed in a word twice, you know. You may have typed in the wrong word. I just read a paper, I think when I was at the doctor's office, that there was an odd that I think was a 4. But, you know, it just didn't make any sense with the odd in there, but with 4 in there, it made perfect sense. So just things like that. So use good proofreading, okay? Now, content also matters, okay? I've been talking about the structural things. Content matters too. So if there's inconsistencies, you'll lose points for that. Now, this is not math class, but I've had more math papers given to me on Pythagorean theorem than I can imagine. And yet, I've had some people state it completely incorrectly, you know. Oh, no, it's the other way around, you know. It was just a dumb one. Someone say, Isaac Newton, I'm just going to use them because I've had a lot of Isaac Newton papers, and he's perfectly good guy to write on. And sometimes they'll say, first time they mention his name, they put in parentheses the year of his birth, the year of his death. You don't have to, but people choose to do that. And then over here on page 2 or 3, they have him dying in a different year than this one on page 1. Wait a minute, it was a long illness, but it wasn't that. No, that wasn't the point. They just were getting the different sources, and they aren't. Or here's one. Something was in 1487, but when they typed it, it became 1847. Okay, no, that guy wasn't alive then. I know he wasn't. You know, that's just sloppiness. So content matters also. Please be careful. Proofread your papers. Read them carefully. All right. Let's get to the bottom of this. The paper is due the last day of class before the final exam, not the day of the final, the last day that we have class. But I don't want all of them coming in that day. I want you to get them done early, get them into me early, and that way you don't put it off till the end. Okay? There's a couple of things. First, you have more time now than you will any time later in the term. Any time later. How many already have a paper due in a mini-term course? Not yet. A test in a mini-term course. No, today's the first day or second day you've been in it. Okay? You have more time now. You have more time this weekend than you will any other weekend. So try to get going on it now. That's one reason. And like I say, I've done this for probably well over 15 years. I've taught every term, summers included, and like I said, I've seen tons and tons of papers. Now, there's a gross generalization. It's not always true. Usually the papers that come in early are my best papers. And as the term goes on, they gradually lose. And usually those coming in late, that say, oh, I got a paper for this one. And then turn it in. No proofing, no anything, no spell check, no grammar check. Just typed it up and get it into me. Maybe late, lost points there, so someone will let us know. Now, I have had some real dogs at the beginning of the term. I've had some great papers coming in at the end, but the general trend is downhill. So get going early, get them done early, get them into me early. Now, here is the stick. If they come in late, after that last day of class, you're going to lose points. Here's the carrot. If you get them into me the month of October, you're going to get 2 bonus points. If you get it to me the month of November, you get 1 bonus point. You turn it in the month of December, you just get your score. No bonus. Okay? So just get, the sooner you get it in, the more likely you are to get a little bit better. This was done for a mini-term, first mini-term, so I'll get this corrected for a second. Okay, now here's one other thing I require that most other instructors don't. When you submit your paper, please attach a single page from one of your sources. Let's say you have 3 sources, pick one source, just one source, and then get 1 page. If it's something you got out of the library, take it over to the copier, copy me 1 page, turn it in. If you got it off the internet, print me a single page. I don't need the whole article. Print me a single page and turn it in with your thing. Now, if you did a computer application or YouTube video that you can't really print a page, do me the link. Okay? Give me the link. And yet, generally, those links I'm going to put on subsequent classes when I teach this course. That's a link that students found helpful for the course. So I do want that link nevertheless, but you don't, it's not a page you can give me from that. Okay. Any questions on the research paper?
Yeah. I got a question.
It's what?
Like, since you wanted 1 page, I could just put my head on either the left corner of the margin or the right corner.
You can do your header however you want to. I'm interested in the content.
Okay. And then question, can I also add a reference page?
Absolutely. I need a reference page. You do need, there's somewhere in here, you will need a reference page. However your format calls for it. Every format has, they call it different things. Reference page, literature cited, bibliography. There's different names for it, but yes, I will need what your sources were. Otherwise, you'll lose points. I'll say sources, okay, because I do need your sources. However you call them. Reference page, literature cited, work cited, there's lots of words for it, but I do need where you got your material. And I need the page from that material.
Oh, like the page from
one of the sources, yeah.
Oh, right, I can just print it off as well?
Yeah, print it off as well. That's what I'm saying right here. I need a page from one of your sources. In addition to your list, that will list all your sources, but I need a single page from one of your sources. Okay. Good deal. All right. Any questions? Other questions? Good questions, by the way. All right. That will be out there once I get the few corrections made to it. That will be out there on Blackboard. And that will be under class handouts and more. Okay? The research paper instructions. Okay. one more. This is my locator card. Now, this is for the first mini-term. This isn't for the second mini-term, but most of this is correct. You'll notice my name's on it, fall terms on it. I'll have second mini-term listed there. My phone numbers are on it, where I am on Monday through Thursday and Friday. Now, Friday of this week, I'm here on this campus, okay? My email address and my department is mathematics. This is natural science too. I teach it both. Okay. Now, this is for this term, but it was for the first mini-term. I'm going to try to get it all on here. I'll try to point out to you the changes. Can I get it all on here? Okay, I think that's as far as I can go. Well, maybe one more. Let me see if I can do one more. Yeah. Okay. All right. Usually I'm on campus by 8 o'clock every morning, Monday through Friday. Most of the time before 8, but usually by 8, okay? And usually I have the first half hour on Monday through Thursday as office hours. On Monday and Wednesday, I have the Math 100 class from 8:30 to 9:45, and Tuesday, Thursday, the Math 112 pre-calculus algebra, 8:30 to 9:45. On Monday and Wednesday, I have a calculus class, which is a 4-hour class, so it goes from 10 until 11:40. So I'm back in the office sometime around a little after 11:45, and there until 12:15 when my Cal 3 class starts, and again, that's a long course. On Tuesday and Thursday at 10 o'clock is a regular 3-hour course, pre-calculus trig, and that's 10 to 11:15. Okay, so on Monday and Wednesday after this class, and sometime during that class I'll have my lunch. Well, not during the class, after the class is over. I'll usually try to eat something here so I can make it through that class and finish my lunch here, and then back to office and advising here. And I'm here till 6 o'clock on Monday. Okay. Now Tuesday, this is the one that's going to be different. This part was the same. In the office, 11:15. My lunch is going to move down to about 1:30. Okay, I'll try to hit the middle of the day. If I can hold out that long till 1:30 and go 1:30 to 2:30, we'll have lunch. And then this class starts at 3:15. That would be right here. And then the lab is late. So Tuesday and Thursday, 4 hours, office hours in here. Sometime in the middle is lunch, but don't worry about that because I usually eat in the office. Okay, Tuesday and Thursday, on Monday and Wednesday, almost the same, except that I have to leave at 4 o'clock to travel to Birmingham East Campus for a physics class that goes until 6:30, and then I go home. Then most Fridays, not this Friday, I'm on the Birmingham campus usually before 8, by 8 o'clock, and I go at least until noon. I say I have lunch from 11 to noon. Usually it's just a snack, and I eat there at my desk while I'm working. So just something to tide me over until I get home. All right. Any questions on my locator corner? I'll get this updated, and then I'll put that under instructor information on Blackboard. All right. Any questions? Okay, that shows to the bottom. Now it'll be going until 7:45. I'll probably be leaving off campus at 8, and the class will go until 7:45. So we're ended at 5:45. The first mini term will be 7:45. Okay. All right. Yes. This was sort of like our lab. We're going to have class the last part. Yeah. Sorry, is your cough real bad? Yeah. If you need to go get something to drink, you certainly can, or whatever. Okay. So I'm going to delete this one. I got one more thing to talk about before we get to the science, and that is safety. There's 3 areas that everybody has sort of have in the back of their mind safety type issues. Some of you have been in my classes before, and hopefully you remember some of these. What would you say one of the areas of safety would have to be? Anything? Nothing?
Evacuation.
Okay, for what? Storms. Okay, weather issues. Absolutely. Now, actually, for a weather issue, we don't evacuate. We stay in the building, but we evacuate the room. What do we do? Let me stay up close to the telephone, to the microphone as long as I can. What is the practice for a storm? If you hear that weather alarm go off, now we're not going to be meeting in here at 11 o'clock on Wednesday or Saturday or something. That's when they do the testing. So if you hear it go off, we assume it's an emergency. Okay? What's the rule for what to do in a weather emergency? Anyone know? Lowest level, interior. So we don't want to be in this room if it's a weather emergency. A tornado, severe thunderstorm, some of those limbs could come flying in the window, glass, people could get cut. So where do we go? Well, here we are in this classroom. We go out of the room, take a left, go down this little half flight of stairs here, take an immediate left, go down another full flight, and you're almost on the lowest level in the building. That's where we go. And we go interior. Now, at the bottom of those stairs, now this is the second floor. First floor is somewhat like this, a little bit different. One of the first things you see when you come out of those stairs are the restrooms. And the restrooms are not a bad place to be in a weather emergency. They're interior, the walls are close together, lots of corners. The greatest strength of a building is in a corner, not in a flat wall. The corner. You have 2 dimensions of strength there. Okay? So that's a pretty safe place to be. Okay? So the restrooms have lots of corners, interior, lowest level. Okay? The downside of a restroom is you probably don't want to spend a couple hours in a restroom maybe. But the worse than that is if it is a severe weather situation in the immediate area, there's a real good likelihood the power's going to go off, right? The restrooms don't have emergency light. So you really may not want to be in a restroom, in a dark restroom for a couple of hours. Okay, so that may not be your first choice. But it's not a bad choice for strength of the area. Okay? Now, so after the restroom, there's actually a couple of more steps down, and then you are on the lowest level. Where there's a corridor here, there's a little office there. It's the academic dean's office on this campus. And she's not always here, but if she were to be here and she would invite you in, that's a safe room because it's interior and it's a small room, so it has lots of corners. Okay? Now here's the other thing that makes the interior of this building particularly good. Down on the first floor, on this side, is soil. Nothing. There's no room on the other side. So there's a lot of strength in that. Nothing can move that wall back there. So this back wall here is a very strong wall. So even if it's not a corner, that's going to be pretty safe. The wind's not going to blow that down. Okay. So, academic dean's office. Now don't break in, but if someone's in there, it's not always her. It could be the associate dean. It could be one of the instructors from the Birmingham campus who's using that as his office when he's over here. It could be anything like that. Okay? Next to that is a large classroom. Okay? Now that's not ideal. That back wall is very good. The corners are very good, but the other walls are not necessarily supported that well, but it's better than being on the exterior. So that big classroom's not bad. If any of you had developmental math, it probably was in 160. You know what I'm talking about? Okay. Next to that, you go into the library space. And just inside the library space, there's a little computer lab. Now that's much smaller than the classroom, so the walls are closer together, more, same number of corners, but they're closer, so there's a lot of strength in that room. Just next to the library is what I call the reference room. That's where the globes are, the atlases, and those kinds of things. That's a pretty safe room, especially that back wall that's against the soil. That's pretty safe. Okay? Don't go any further than that, because after that, you're on the exterior. You don't want to go on the exterior. You want to stay on the interior. Now, left off maybe the best one to go, period. And that's the hallway. Again, it's interior. The walls are relatively close together. And here's the advantage of the hallway. It does have emergency lighting. whereas those other rooms do not. And you don't have windows, you're not staying away from windows, so you're on an interior space with that goes going to be completely in the dark if the lights go out. But these have battery-powered emergency lighting. The hallway does, so that's probably going to be the place of choice. But the other rooms aren't bad, especially if you have one. Okay. Now, if there were a situation that does go off, someone else is going to lead the way down there because I'm going to make sure the last person in here, maybe this gal who had a bad cough, she may have stepped out. I'm going to wait till she gets back so everybody gets down there. So you get down there, stay together to begin with. Wherever you choose to go stay as a group, because when I go, I'm going to carry the roll book. And when I get down there with that last student going down there, and maybe somebody has sprained an ankle or twisted a knee or something and is on crutches, I'm with that last person going down. And when I get down there, I call the roll. If someone's missing, either I have to come back up or some emergency person has to come back up and risk his or her or my life or health, searching the rooms, trying to find where we lost the student. But we don't want to lose students. So hang together. Once the roll's called and we get information, then you can go mingle with friends and stuff like this. But you do not want to go, oh man, the dog's outside, I need to go get her in. No, you don't. The dog will take care of herself. You need to stay in the building. A car is just about the worst place you could be in severe weather. It can get blown about, and power lines can fall on it, trees can fall on it. In fact, wasn't it Hurricane Michael that the first death I heard about from Hurricane Michael was someone in a car, a tree fell on the car, they got trapped, and before they could rescue them, the person died. Okay? Cars are not safe places to be. Interior parts, lowest floors of buildings, those are the safest. Okay, so there's our weather emergency. What other type of emergency might we be concerned with? And this one we would evacuate. Fire, exactly. I'm going to group with that things like chemical spills. Hopefully we won't have either one, but if there were, let's take worst case scenario. The fire starts in this room. Let's say my computer blows up and catches those papers in the desk on fire. What do we do? Okay, someone said run. Yeah, we get out of here as fast as we can and leave the building to burn and everybody else to suffer today, right? Oh yeah, okay, I like the way of thinking. Okay. No. Okay, what do we do? Say again? Okay, have a bonfire, is that what you said? No, that's not either. I don't like the way of thinking either. Okay, okay, very good. Somebody, now here's something, I don't know if you've had this in orientation or not, but there is a cell phone or radio or something like that that the duty police has on his or her belt always, wherever they are, whatever they're doing. That's the best number to call, okay? And I believe you can get it at the on the website somewhere. I can't remember exactly where I've heard that it is, but there's some place, probably on the Lawson app, the Lawson State app that we have. That emergency number is right there. There's one for Bessemer, one for Birmingham. That's the best thing to put on your cell phone as a number that you can dial immediately. If not, 911 is next best. But the best one is Lawson State. They will get in touch with 911. So the best is going to be that number for Lawson State Police. Okay? So yes, somebody is doing that. That's one thing we warn people. But what else do we need to do? If the fire starts in this room, say again? Okay, we will get out of the room, guaranteed. But we don't want the building to burn down and everybody else get trapped. What do we do?
Small fire, I pick up a small person.
Oh, I see. Okay. Okay. Huh? Yeah, I know. Fire alarm, of course. So, here's the thing we need to be thinking. Where's the closest fire alarm to room? Anybody? Anyone know the closest fire alarm to the room? Guess what? Everything you see on this diagram is not on this part of it. Anyway, this big horseshoe here, that's the old part of the building, not a fire alarm inside. This old part of the building was built before the fire code was required. So there's not one here. Okay, so here's where the closest one is. And my recommendation is 2 people go to do the fire alarm. In case one person trips and falls, the other one can still get there. Okay? Okay. Go out the room, hang a left, go down this half flight of stairs. This time go up to this corridor that goes across to financial services. That part of the building, that first floor down there, that part of the building is the newest part of this building. When that was built, they have fire alarms right here and right there. You look in, you go through the corridor on the left or the right, you can see the fire alarms right there. That's the closest. That's where you go. Someone goes and pulls the fire alarm. Okay? Now, what else might we choose to do? You said put a student over the fire. Probably something better than that. I know. Exactly, I understand. But what might we do to help put out the fire? A fire extinguisher. Now, where's the closest fire extinguisher? Anyone know? Okay. Guess what? On this one, you couldn't be much better. 5 feet from where I'm standing, right there is a fire extinguisher. So someone else, okay, somebody's dialing 911 or the campus police. Somebody's going down to pull the fire alarm, and somebody's going out there. I know you guys have probably always said, "Oh, wouldn't it be so cool to break that glass with that piece of metal there?" You know, haven't you? Sometime in your life, thought, "Hey, that'd be neat to do." Yeah, you get to do it now. Okay, if there is a fire in this room. Okay, someone get the fire extinguisher. I'll handle it if no one else wants to. Although I have been trained on those things before, but they're pretty simple. So I'll take care of that. Okay. Then, now we're ready to leave. Okay. And probably some of you have already been leaving. Where do we go? Okay. Yeah, to a gathering point. You're absolutely right. And where do we go? Come on in. We go out the door here, hang a left, go down that half flight of stairs, hang another left, go down a full flight. This time you don't go into the building, you go out of the building. And you go out of the building, and here's the diagram. Not a particularly easy one to see. Here we are in this classroom right here, and we go to that parking lot right over there. It used to say we go 75 feet from the building out that way, and that would be the grassy area, which would be pretty nice under the shade tree or something like that. But now they want us to go in the parking lot, which is not shady or anything else. But anyway, that's where we go. And we stay together as a group because when I get out with that last student, after I've put out the fire, or done everything I could here, I go out with my roll book. I'm calling roll. If we're missing anybody, someone says, "Hey, fire in the building, no more class today, I'm out of here." If that happens, we can't account for you. Someone has to go into a burning building, risking his or her life and health, looking for you when you've gone somewhere you weren't supposed to. Don't do it. Stay together in a group. They'll get the word to us. If it's indeed going to be something, hey, yeah, go home. There's nothing else we can do here. Then you leave. Okay? But you don't do it on your own. Okay? Stay together as a group. Okay? So any questions about fire? That also, now here, why do we get at least 75 feet from the building? What if something were to explode in here? There goes the glass that way. You don't want to be near the building. Get away from it, outside the range of glass particles. Okay. Any questions about fire or chemical or any kind of internal emergency you get outside? That you do evacuate. There's one more other safety issue I never used to even consider or think about. But in today's environment, unfortunately, we have to do this. Say again? Anybody?
Gunshot.
I'm sorry?
Gunshot.
Yeah, active shooters. Okay, hopefully that will not happen here. But it has happened at one community college in the U.S. That's the only one I've heard about. Several of the big universities have had them only one community college. I can't remember where it was several years ago. Okay? Now, here's the thing. I'm hard of hearing. So you're going to hear it before I will. Okay? So if you hear a pop, pop, pop that you think could be gunfire, let me know. Okay? What is it we got to do in case of active shooting? Okay, let's not jump out the window. Okay? There we have more injuries to write up than maybe it's worth. Okay, so let's not do that. This is the second story. What do we do? Okay, that emergency number, we start calling it. Probably other people are calling it too. If we're the first to hear it, first to think of responding for it, then let's get that phone call made. Okay? Now, what else do we need to do? What do we need to try to be aware of?
Don't go to it.
What's that?
Don't go to where the.
Yeah, don't go to where the shooter is. Now, here's the good news, folks. I have a key that will lock this door. Not all instructors have keys to the classroom. I happen to have a key to this one. The bad news is I can't lock the key from inside. There's no button. There's no key. I have to go to outside and lock the door from the outside. And then I come in. Don't you be pulling the door closed. Okay. All right. So I come in. So I get the door locked. Here's another bit of bad news. There's another classroom right through there. Okay? And go right through. This door does have a button. You press it, and it locks from the outside, not from the inside. That locks us in, but doesn't lock the shooter out. So don't lock this door. All right. This door is the window, right? Okay. This door has a deadbolt. I don't have a key for that. Okay. So that doesn't do us any good. However, the next door does have a button, and it locks from the outside, not the inside. So we do press that button and lock that door. Now, there is another classroom door coming in to that classroom. I don't have a key to that. So we close that door, turn off that light. We want them to think nobody's there. We lock that third door. We close this door. The reason for that is that one has a glass, this one has a glass. He can see through. If we close this door, he can't see through. Okay? We close this door also, and where do we go? Out the window. No. Okay. The best place for us is right back here. Because he can shoot through the glass, he can shoot through the door maybe shoot through this, he can't shoot through concrete platform. Okay? If he tries, he's going to get packed pressure thing on him. So hopefully that was it. And we're very quiet. We turn off the lights. We want him, if he does look in, finds the door locked, looks in, doesn't see, doesn't hear anybody in here, he goes to another room. Okay? And he doesn't try anything. Okay? We're as quiet as we can be. After we dial that 911 or the campus police, we turn our cell phones off. Silent. We don't want mom and calling say, hey, I heard there was a shooting. Yeah, we just take in the room. No. We don't want that to happen. Okay? So we just stay put as long as it takes until we're certain security has come through and said all is clear. And then they'll direct us how to get out. Okay, we don't want to think about things like this, but we've got to. Okay? Hopefully it will never happen. None of those will ever happen, but they could. Weather especially, we have no control over that. All right, now let's go back to fire. If it doesn't start in the room, if we do hear that alarm go off, and it is a fire, then we proceed out. Like I said, I'm the last one out of here. I've got my roll book. We go as a group. If it starts in here, we've got some scattering to do until we get back as a group. Okay. Any question? Now, a couple times people have brought up the issue of what if the shooter does make his way into here? You don't be the heroes. Okay? You're young. Yeah, okay, good. Hands to me. Oh, okay. Your lives are ahead of you. Mine's mostly back this way. Okay? So if there's anything to be done, I'll be the one doing it. Okay? And God will, risk yours. You're more valuable than I am. I'm pretty expendable. Hey, I've only got a couple more years before I'm retiring, so they can get by without me. You're the future. I'm the past. Okay? So don't mess with it. All right. And I was in the Navy, not that I learned that much, but I did stand watches with the SEAL. And I had a quartermaster who was bugging him one night. I bet you don't mind being in a bar fight, because you know how to really hurt people. And so he said, the last place I ever want to be is in a bar fight. So he said, when we fight, we want to control as many of the variables as we can. Bar fight, there's no control of anything. He said, oh yeah, but you still would know how. He said, no, I'm going to get out of there as fast, as safely as I can. Oh, but you got to know something. He said, well, there are a few things. If the guy is really in my face and I can't get rid of him, this sounds pretty gross, folks, but this is what he told me. He said it only takes a few ounces of pressure to pop someone's eyeball out. So do that, and while he's reacting to that, get out of the building, get away from the situation. And he said if you can't get to there, it only takes about a few pounds of pressure to pull off here, hand it to him while he's figuring out what to do with it. Get out of the room, get away from the thing. So I'm not necessarily going to do any of those things, but at least I've thought about them. Okay, so anyway. We won't go there. We stay quiet. We don't want the confrontation. Avoid the confrontation. Okay. All right. Any questions on safety? Okay. Then I think I'm going to close this out, and let's get started on the real issue. Okay. Does anyone need a break before we get started? Let's see. Yeah. We got started at what, 3:15, and it's now 5:15. So we're not halfway through yet, but we have started. Do we need to take a little break? Let's do so. Try to get back in less than 5 minutes if possible. I'm going to put this on pause. And by the way, folks, let me also tell you this. I've got to call roll twice, once for class and once for lab. So remind me at 5:45, I've got to call roll again. All right, we are now recording again. And by the way, I am notorious for forgetting to turn the recorder on, because I turn it off when we go on break and forgetting to turn it on. If you see this, and you might not be able to see the numbers clicking by on a clear background, you could. Let me show you what it looks like. Clear recording, let me know, because otherwise with folks at home that might be missing class, they're not going to be able to pick up on it. Okay. Any questions on anything before we get started now? And remind me at 5:45, I've got to mark the roll again, because they require attendance for class and attendance for lab. This crazy system we have. Okay. Now, chapter 1. I don't know. A lot of science books usually start off with a sort of a nebulous kind of chapter like this. What is science, And the first time I taught the course, I thought, what's the point in doing that chapter? Then I found out some of the concepts we talked about later were introduced in that chapter, and then I had to go back and pick them up. So we're going to get through this and hopefully do it fairly quickly, just to give you the basics, foundation for what we're doing. The core concept here, and this is on page, if you got your text. Now, some of those were the little books. They may have two different numbers. I'm guessing with this one, they're going to be the same most of the time. In the second course, which is the Physical Science 1, they have sequential numbers in one place and then the book numbers in the other. So when I was talking about page numbers, you just didn't know which one I was talking about. I hope for the first 4 chapters anyway, these are going to be the same. But on page 1, at least in my book, the core concept is science is a way of thinking about and understanding your environment. That's basically what it's all about, okay? And what is your environment? Okay. One thing is what you do. Okay. You're trying to produce vehicles that will move, right? That will have velocity, speed, acceleration, exert forces, control themselves, as in braking and steering and things like this. Science is involved with every bit of that, okay? In addition to other things. Drinking a drink, eating a candy bar, whatever, science is involved with that too. You're metabolizing, you're using energy, you're changing energy forms. Science is involved with it all. Thinking about and understanding your environment. And a lot of what this chapter is going to be doing is giving us a framework from which to think and from which to build. So, these are sort of, to me, sort of wanky kind of definition. A search for sense, in some sense that makes some sense, okay, a search for sense. Finding order out of the surroundings, yeah, that probably is somewhat true too. Some people think of science as tools and rules. It's not a very good way of thinking of science, because science involves a lot more than that, okay? Now, they don't say why they're giving this picture here. It looks like an average college campus somewhere. You'll notice most people are moving. That's science, okay? The friction that enables them to move, the friction that enables them to start moving, the friction that they're having to overcome to move, okay? All that's going on here. They're going at constant speed, increasing speed, decreasing speed. They're carrying different packs, so they're supporting weight. Variety of things going on here. I can't think of any other reason for that to be there except science is all around us. Science went into building the buildings. Science goes into how the trees live. Science is just about everywhere. Here's the overview of the entire chapter here. The first part of the chapter, we're going to be talking quantitative. Remember I said this first test is going to be more quantitative than it is other. The test questions, the test bank had nitpicky little questions over this kind of stuff that I had to really think about. I'm not sure I would have come up with the answer they were looking for. I thought, this is not what I'm trying to test here. So more of this first test is going to be on the quantitative end. There will be a few questions perhaps on the other part, but mostly on the quantitative. So what we're going to look at are objects and properties, the things that we will be measuring, the quantifying properties, how we'll go about measuring things, the different measurement systems we have, specifically the metric system, the standard metric units, and the prefixes in the metric system, and then what are some things we can understand from our measurements, okay? And we'll be doing the little sort of, it seems like kind of dinky things we'll be doing here. We'll be doing the same type things with a lot more meaning in subsequent chapters. So that's why this is a good start. Then the last part of the chapter, which is really a fairly short part, is a little bit on the scientific method, which has some value to think through that. Explanations and investigations, and basically the rest of this is just sort of nomenclature so you know the language that we're talking about. Laws and principles, what's the difference, how they're similar, models and theories, how do those work too, and we'll look at a couple that are fairly interesting to see. So that's the overview of the whole chapter. Let's start with objects and properties. What are objects? Anything that you can see, touch, feel, measure, weigh, do anything with. That's an object, okay? And most of what we're going to be dealing with is dealing with objects, okay? How fast the car is moving, how fast the electron is moving, whatever it is that the thing is, usually we're going to be trying to measure some characteristic of that thing, okay? Now, properties, those are the qualities or attributes. So let's say the object in this old desk here. It's been here a lot longer than I have, okay? It was in the room old before I ever started teaching here, so it's been around a while. That's the object. What would be some of the properties of that object? Anything you could think of. Describe that desk. Okay, what's it made of? It's made of wood, okay? That's pretty obvious. Looks like oak wood to me, too. Anything else? Okay, you can measure its height. That would be a very good measurement to make. What would you say its general shape was? Rectangular, a rectangular solid, or at least the void under here. So yeah, there's several things you can do. Not just its height, its width, its length. We could measure all of those quantities. Those are the properties of that desk, the qualities or attributes of that object. Okay. Now here is a word that before I started teaching from this book, I don't think I'd ever heard of it before. In fact, when I first read it, I thought they were misspelled it. I thought they were saying reference, but they're saying reference with a T in there. And these are things that you refer to. Comparative properties and other more familiar objects. Now these are really lame examples. Sky blue, lemon yellow. Okay, right. I've seen some lemons that are almost greenish looking. I've seen some skies that are very gray. So those are not extremely good, but they would be things to refer to. Now, I was born in North Carolina, so when someone says Carolina blue, I know exactly what they're talking about because that's the color the Tar Heels uniforms are, is that pale blue Carolina blue. That to me is far more specific than sky blue or lemon yellow. But those are not the major reference. The major reference, someone said the height of the desk here. How would you measure the height of the desk? Say again, a ruler measured in what? Okay, inches. That would be one way. That would be your reference, the inch. How many inches tall is that desk? But if you were metric, you might use meters with so many centimeters, as a fraction, okay? You could say, how many staple lengths are there? Okay, 1, 2, 3, you can measure it in stapler lengths. That could be a reference, a rather strange one, but it could be a reference. So whatever the comparative object you are to what you got. How do they measure a horse's height? In hands, okay? I don't know, are they spread out hands or are they closed hands? I don't know. But I know they measure so many hands high. So there are a lot of rather strange references that are out there. Okay. Now here's the problem with these various things. The language can be subjective, like sky blue. Well, if you were in Seattle, you might not ever see much of a blue sky. So you might not know what someone from Montana was talking about if they said sky blue. Okay? So language can be subjective. It can be ambiguous and sometimes even circular in the reasoning or the logic. So you have to be careful. In science, we try to be very specific. So we don't use some of the sort of nebulous, often common terms. We try to do something. So our quantitative reference are the units. Okay? Now, I'm going to give a dumb example, but we're going to use more of it. Let's compare the reference unit with the property being described. Say, someone said the height of the desk. Now, what are some length measurements we could use? Some units for length. Name a few. Okay, someone said inches earlier. Feet. Okay. How about miles? That's a length measurement, right? Would you want to measure the height of the desk and what fraction of a mile that was? You could, but no. A mile is really long. This is not. Inches would be far better. Feet would probably be the best, or one of the best. Yards, that might work too. Meter would work. Centimeters work. Kilometers, nah, you wouldn't want to use that. So you, yeah. Millimeters, yeah. Boy, yeah, you have a big number there to deal with. Comparing the reference unit to the property being described. Now, if you were talking about the distance in an atom between the nucleus and the electron's orbit, you wouldn't want to use miles there either. In fact, a millimeter would be too long. You would go down to a very small unit, as in a nanometer or something like that. Okay? If you were talking about the distance from here to Tuscaloosa, millimeters would not be a good choice there either, would it? Boy, you'd be counting forever to get how many millimeters between here and Tuscaloosa. Miles or kilometers would be far better. So comparing the reference unit to the property being described, getting something that makes sense. Okay? following a procedure specifying how the comparison is done. Now, let's say we did use stapler length. Okay, that's a weird reference. But if you want to know how high the desk was, you could say, well, I'm going to put it there, put my finger here, and then measure 1, 2, 3, 4, 4 and a fraction. Stapler length's high. Okay, that's a dumb way, but you'd have to follow a procedure specifying how the comparison is to be done. Okay? And then, like I did, counting how many of those standard units to describe the property under consideration. So that's why you would want to use a reference unit that made sense for the height you were dealing with. Okay? Now, this is essential. When you're talking about any kind of measurement, okay, a number is not adequate. If you just have a number, but without the referent unit, it's just a number. Okay? Believe it or not, there have been some incredible errors made because either people didn't put units down, put the wrong unit down, or assumed the unit that they were dealing with. I'll give you one. Now, I don't have the numbers specifically, but this did happen. Okay? Back in the 60s, I know y'all weren't around then, but if you studied any history, okay, some of you weren't, okay, we were in, as soon as World War II was over with, we were in another war, the Cold War, okay? And there were many ways the Cold War kind of exhibited itself, okay? There were all sorts of things. The Berlin Wall was built, you know, all sorts of things. The Iron Curtain, you know, they talked about it really wasn't an Iron Curtain, but there were things done. But one of the, it's sort of a positive thing, but it was all part of the Cold War, was the space race. Because in World War II, the people who were really far ahead in rocketry, projectiles and things, the Germans. They were way ahead of us, way ahead of the rest of Europe, way ahead of Russia. They had scientists who had been working on rocketry and sending things into orbits and things like this, specifically weapons and stuff, and they were way ahead. I mean, they were bombing London with their, what was it, V-12, was it, rockets or something like that. I mean, just, you know, not risking a single airman's life, firing these things from, say, Belgium and places like that across the English Channel and just wrecking London like crazy, okay, without any risk of a pilot's life, okay. So, at World War II, at the end, to the victors belong the spoils, right? So one of the spoils of the war was all these German scientists. And the West grabbed as many as they could, and Russia grabbed as many as she could. And they put them to work building rocket programs and space programs for themselves. If you look at the names, Oppenheimer, goodness gracious, von Braun, yeah, they were all over the place. And in Russia, they had theirs too. And then we got into the space race with Russia. And Russia started kicking us. They got into space first. They got the first orbit. They got the first monkey or rat or dog or cat or something into space and brought them back alive. They brought a few back dead too. But they got the first man into space. They got the first orbit of space. They did a lot of things first. Well, we got really upset with that and established NASA, National Aeronautic and Space Administration, okay? And NASA was basically, John Kennedy said, we're going to the moon in a decade. He set that as a goal, and they were going to pour as much money into it as they could to get us there. And we barely made it, but we got to the moon within that decade. Now, in the process of doing that, NASA was given as much money as the country could afford to give them to build the things, to test them, to do all the stuff. But after we made it to the moon, the Apollo missions, is that me or somebody else? Okay. After a while, Congress, especially conservatives in Congress, decided, hey, we're spending too much money here. We beat the Russians to the moon. We accomplished that. We did. They said, hey, we got to scale back. We can't just give NASA blank checks anymore. So they said, nope, you're going to have to do your projects more efficiently. So rather than you spending as much money as it takes for you and your scientists to do it, you need to farm some of this out to universities, to national laboratories and things like this. Send it out on a bidding process like lots of other projects are done. So they did. The first thing they did this on was a Mars mission. It was one of the Mariner missions. I don't remember which one. Anyway, they wrote out the request for proposals and these kinds of things, and various universities and national labs and other consortia got together and bid on the different pieces. One team was to bid on the launch. Another was going into the Earth's orbit. Another was to approach the moon. The other was how to land on the moon. You know, and different ones took different pieces. They broke them up. They got their expertise together, and they bid on them. And they came up with a project. Much cheaper than NASA had ever done a project before. Okay? Maybe 4 or 6 billion, something like that. Sounds pretty cheap to me, doesn't it? No. But much cheaper than it had been. So anyway, the launch went perfectly. Got into Earth's orbit perfectly. Transitioned like a charm. Made its way from Earth toward Mars, and that's a pretty complicated thing if you figure these planets are going far distances apart. Got to Mars perfectly. And then started orbiting, went to orbit Mars, went to the next thing. The craft twisted, turned, and crashed right into the planet. Wait a minute, what happened here? $4 to $6 billion went crashing into the planet. They just barely got a few instruments up and took some measurements on the way down and got a few of those transmitted back to Earth. Got almost no useful data. Well, useful data on how to get to Mars and stuff. What happened? It didn't. Oh, yeah, that was it. Okay. No, actually what happened is the team that took the information from the previous team getting to Mars, and then the team that was supposed to get them in orbit of Mars, was assuming this team was using English units and they were using metric. Really? Yes, really. Because someone had to put the units down. And they just made the assumption that they were using the same units they were intending to use. And with that wrong, right number, but wrong unit because no unit was listed, crashed right into the planet. Okay? I hope that you are someday in a position to make that $4 to $6 billion error, but don't make one, okay? That would be nice to have that kind of power and to be in that kind of, but it wasn't a very nice thing to happen. And that is a true story. I may have the numbers wrong, but that really did happen. Okay? Yes?
Did you call it wrong yet?
Is it 5:45? Yep, it just is. Okay, thank you for catching that. All right, and I'm also learning people's names and faces. Isaac? Okay. Hi? Gotcha. Gary? That's you, okay. Okay, has Michael A. Davis come in? No. Dalton? Okay. Colton? Got it. Melanie? Right? Okay. And Stessany? Hunter? Okay, got it. Thank you. Has Tyler Scott Latham come in? No. You're saying? Got it. Thank you. Justin is here. Trent? Which one? Okay, got it. Thank you. Demetric still here? Jose? Cody. Got it. Thank you. Patel. Taylor. Got it. Thank you. Peyton. Got it. Thank you. Chase. Got it. Mac. Got it. Thank you. Zachary. Got it. Kevin. Got it. Thank you. Steve. Got it. Thank you. Spencer.
Here.
Okay. And it was Spencer, not Spence, right? Spencer. Okay. All right. Brian S. Thrasher. Did he ever make it in? Renee Threadgill hasn't. Sarah hasn't. And Clinton Lamont Wilson. Did you make it in? No. Okay, so as far as I can tell, we haven't lost anybody. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 2, 4, 6, 8, 10, 12, 14, 16, 18, 19, 20, 23. Got it. Good deal. Okay. Thanks for reminding me. Okay. Now, what are our standards? We don't use staplers as our reference. The measurement systems are all based on some type of standard unit. We've got two major systems. There are other systems out there. These are mostly the ones that we deal with. Now, back when I was very young, everything was done in English systems. All of our vehicles, American-made vehicles, were all 3/4, 5/16, 7/16. Everything was based on English measurements. Are any car parts on English measurements anymore? Not a one. American-made, foreign-made, none. Why? If we're going to sell cars overseas, we've got to use the units they use. And we're the only industrialized nation on the planet that uses, on everyday use, the English system. The English don't use the English system anymore. I mean, yeah, on everyday life they do, but their official system is the metric system. Our official system is still the English system. Now, many of these units are based, unfortunately, on parts of the human body. Some of them are pretty obvious. A foot is basically about the average of a man's foot length, okay? Approximately, okay? This tile is 1 foot, so that's awfully close. Mine's a little bit longer, okay? So that's a foot, okay? An inch is about your thumb joint. Now, of course, some people have bigger thumb joints than others, but that's about an inch, okay? A foot. A yard is approximately the distance from the tip of your nose to the end of your finger when you hold your hand out there. Now, y'all are probably too young to remember this, but if you ever went to a hardware store where they also had women's, things like cloth and stuff like that, buttons and things like that for sale, the little ladies that used to measure it, if you wanted 3 yards of fabric, they do 1, 2, 3, and they give you a little extra in case the arms are short. That's how they estimated a yard of cloth. 1, 2, 3. Okay. Now they have tables with exact measurements and cut down, if you've ever seen that. But in the old days, I remember seeing the ladies do that and wondered, how do they know that? Well, that's about a yard. Okay. By the way, anyone know what this is? From your elbow to your tip of your finger? Any of you built an arc lately? Cubit. It's a good old biblical term, but that's a cubit. Okay. Approximately. Okay. There were other things, but many of those are based on human body parts. Okay. Different units were not systematically related. How many inches in a foot? Well, how many feet in a yard? 3. How many yards in a mile?
A lot.
1,760. Oh, nice round numbers, right? No. Don't make it. How many ounces in a pound? 16. Not 12. Okay. How many pounds in a ton? 2,000 pounds. We hit a round number. Okay. Goodness gracious, where did these come from? Now, if you go into fluid ounces, that even gets weirder, okay? And, yeah, the English system is not very uniform, not systematically related, okay? Now, the metric system. There originally was a metric system. Later, they adjusted it and called it the SI system. Does anyone know what SI stands for? Yeah. Yeah, it's actually in French. In French, a lot of times the adjective follows the noun. It doesn't come in front. We would say international system. In French, they say système international or something like that. I don't speak French very well. Okay? So that's what SI stands for. Now, when someone talks about the metric system, most of the time, the basic unit is the basic unit, right? Meter is the basic unit of length. Gram would have been the basic unit of mass, okay? In the SI system, that's the one place that the one basic unit, kilogram, is not just gram, it's the one with the prefix, kilogram. Because a gram is a tiny little amount of mass, really small. Kilogram would be about, maybe on the book would be a little bit more than a kilogram, maybe close to 2 kilograms. But, you know, it's a lot more massive, okay? So that's what the SI. Everything else is a basic unit. Meter for length, kilogram for mass, second for time. Now that's the strange one here. Since everybody uses time about the same, that's a very non-metric system. You know, in metric. Because how many seconds in a minute? Yeah. Everything else is base 10 and time is still 60. Now who do we blame that on? The Sumerians. They were ancient people long before the Babylonians were around, but from the same part of the world. And they, for some reason, were a base 6 country. I don't know why. But that's why we have 60 seconds in a minute, 60 minutes in an hour, 60 seconds in a minute of a degree, and 60 degrees, and 360 degrees in a circle. You know, everything had a 6 in it somehow. And somehow that got to us. So that's the one metric unit that's not very metric. Now, when you get smaller than a second, you talk about microseconds, milliseconds, and things like this. So everything small in, that makes sense. Ampere, okay, unit of current. Kelvin, the unit of temperature. Mole, a unit of chemical mass. That is not really mass, but amount of material chemically. Candela, which is a measure of light intensity. Okay, those are your 7 base units in the SI system. In the old metric system, it would have been gram. SI system is kilogram. Okay, everything else is based on those. Okay. Now, if we think back on the English system, what's our basic unit for length in the English system? Foot. Okay. How about mass? Pound is a force unit, not a mass unit. We don't use a mass unit in the English system. We have one, but nobody in the world hardly uses it. You probably don't even know what it is. Anyone want to hazard a guess what the mass unit is in the English system? A slug. That's it, a slug. Has anyone ever gone to the store and said, I'd like 3 slugs of sweet potatoes, please? No. Huh? Do you have one? Okay. Yeah. In fact, it doesn't even have an abbreviation. If you ever use a slug, you have to spell it out because it's not even an abbreviation for it. We just don't use mass in the English system. We should. It's a fundamental unit. We use second, it's the same. And we use ampere, it's the same. Now, I wonder why. Well, let's go back. Notice when the metric system was established, 1791. What was going on in the world about 1791? Anyone recall? What had just happened? 1776, what happened? Yes, American independence, okay? And what country helped us in our reach for independence? Several did, but one in particular. Second? England was who we were fighting against. Yeah, who always fought against the English? France, if they had an excuse to. So France helped us in the American Revolution. Lafayette, remember those stories? And then shortly after the American Revolution, what happened in France? The French Revolution. Okay? That was right about this time. Okay? Now, here's one of the reasons. England was a very small country. And because it was fairly small, very populous, small, they could sort of control everything. It was very centralized. France was a much bigger country. The people in Brittany didn't really like the Normans that much, and the people in Normandy didn't like Alsace-Lorraine, and no one liked the people from Paris. I mean, and they always tried to cheat each other. So their units, which were probably similar to the British units, the English units, it was just a madhouse, especially when the French Revolution happened, and everything was a madhouse. So they decided, the scientists got together and said, look, we need to standardize our measurement system. So everybody uses the same thing. So in 1791, someone had measured as well as they could measure the length from the North Pole to the equator. Okay? I don't know how they did it, but they measured as closely as they could. And one in millionth of that, or 10,000th of that, or something like that, they said that will be a meter. And that's how they came up. And meter in French means to measure. That's what it means, to measure. And a meter turned out being just a little bit longer than a yard. Now, they didn't use body parts, but just as a reference, from your other ear to the tip of that finger, that's about a meter. It's about 3 inches and a little bit more difference between a meter and a yard. So a 100-meter race is a little bit longer than a 100-yard race. Okay, okay. So that's where that came from. And then all the others were based on the meter and the fractions of meters and things like that. So that's how the SI, System International, French words because it came in French. Well, about that time was when electricity was being developed and studied, and because France was the dominant culture at the time and had the most advanced culture, they had the better scientists, and Louis Ampere did some of the early work here and came up with the unit for current, and they named it after him. So, electricity began at the same time they named it. So why the English didn't already have a unit for it, so everybody adopted all of the units in electricity and magnetism universally, pretty much. Actually, magnetism has been around a little earlier, so there were some earlier units for that. But electricity, what? So the volts the same everywhere, the amps are the same everywhere, coulombs are the same everywhere. Coulomb was another French guy. Ohms was the German guy. All those, and they're all metric. Because we talked about kiloohms, milliamps, right? They're all metric, even in English units. Okay. Kelvin was the temperature. We'll talk about that in the temperature. We probably won't get far enough in chemistry to talk about a mole, but that's the standard, and we're not going to do light intensity, but that's the standard. All the other units are based on that. What is velocity or speed? The distance divided by time, right? Meters per second, miles per hour, kilometers per hour, centimeters per second. Yeah, something like that. Distance divided by time. What's acceleration? Okay, that's meters per second squared. Distance divided by time again. What is a force? A force is a mass times acceleration. It's a kilogram meter per second. So all the other things that you measure anywhere are based on those 7 entities. Okay? So we'll learn that. We'll follow up on that in later chapters. So let's look at these metric units. And we're only going to consider 4 of those properties that we were talking about before. There were 7 there before. We're only going to deal with 4 of them for now. These are length, mass, time, and charge. Okay? Actually, we're not doing charge, we're doing current, but they say charge. Okay? Length and time we're going to deal with in the next chapter mostly. Okay? Then mass will come into play in the following chapter. Okay? And then in chapter 6, we'll bring in current and charge. And the other things there.
Is that the stopping point?
No, it's just his stopping point. Okay. Yeah, dream on. Okay, no, I mean, yeah, okay.
So this is where we're at?
Huh? This is where we're at right now, but we're going to go further. Okay. All right? Now, this is one of the weirdest things. This is our reference for length. No one uses this, but this is the gold standard for length. The distance light travels in 92,458 of a second. Okay? Yeah, right. That's what we measure. But actually, that's how they define length. Much, and that would be what a meter is, I think. Okay? What they really use is stored in a vault in Paris, because that's where they came up with this. I believe it's the Louis Pasteur Institute, maybe, or maybe one of the Curie places, or somewhere like that. They have a vault that's hermetically controlled, the temperature, the humidity, everything is strictly controlled and locked up within things, locked up within things, locked up within things, is this one length of some type of material that doesn't corrode, doesn't expand, doesn't contract, and that is a standard meter. And all the others are based on that, and are based on ones that are taken from that. Okay? But that is how it's defined, how far light travels in that fraction, tiny fraction of a second. Okay? Because the speed of light is a constant. It doesn't vary anywhere, anyway. So that's why they use light. Okay, mass. Okay? Now, where mass was originally came from, remember they had a meter, okay? And they decided to split that into 100 units. That was called a centimeter. Now, a centimeter, by the way, this isn't how they define it, but a centimeter is approximately the distance across your little fingernail. An inch is about the length of your thumb joint. This is approximately your little fingernail, the width across there. So you have a cubic centimeter would be a cubic centimeter long, a centimeter high, and a centimeter wide. Okay, so that would be a cubic centimeter. And if you took the most common material on the surface of the planet, water, and 1 cubic centimeter of water, they define to be 1 gram. That's where they got the unit for mass. Okay? Well, that's not very precise, but that's what they did. Now they take a standard metal cylinder, again, that's made out of a certain metal. It doesn't corrode, doesn't do anything else. They have it stored inside bell jars, inside vaults, inside things, all controlled, and that's your standard kilogram. Because a gram is a tiny, tiny amount of matter. So that's your standard kilogram, your mass. Okay. That's different from weight. Mass is how much material is there. Weight is really a force, and it depends on what gravitational field you're in. And the gravitational field where you spend your whole life, I've spent my whole life, is the Earth's gravitational field. So mass differs from weight only by the acceleration due to gravity, which is pretty much a constant anywhere on the surface of the Earth. Now, if you go into outer space, do you weigh the same thing there as you do on Earth? No. You almost become weightless if you go far enough out. But even the ones going around the Earth, in a space station or something like that, they have some weight, but it's very much less. They say they're weightless, but they're really not. Okay, but their mass is the same. Mass is a constant. Okay. Time. Oh boy, you talk about a weird one. The reference for that is the oscillation of a cesium atom. Now, cesium is a radioactive atom, and so it's easy to determine its oscillation because of its radioactive nature. Yeah, I'm going to set my clock by that. No, they have other ways to compare it, and they do that. Now charge, even though the unit is for current, not charge, but they're related, we're going to do that in chapter 6, okay? The electricity chapter, electricity and magnetism. All the other properties that we're going to be using in the first, well, in all the chapters we do, except possibly chapter 8, are going to be derived from these 4, okay? The first 3, chapters 1, 2, oh, they did leave out 1. Chapter 4 is going to introduce this one, that's temperature. We'll go back to Kelvin and the other scales for that. Chapter 6, then we'll introduce the electrical units, okay? But all the other properties are related to those here. Volume is length times length times length. Cubic meters, cubic centimeters. By the way, a little trivia question out. I think this is true. I've been told that it's true. One of the, I don't want to say first, but one of the earliest of the Japanese cars, not maybe the first, one of the earliest of the Japanese cars was actually built by a Japanese company that had been making motorcycles. That was the primary means of transportation they dealt with, but they decided to grow up in their car. So the very first engine was an old motorcycle engine, beefed up a little bit, and they named their car after the unit. Now, what do we refer to when you talk about an engine? How do you measure an engine? Okay, so many cubic inches, cubic centimeters, liters, whatever, right? What are you measuring? What are those referring to? That's not the volume of the engine, is it? It's the volume of your cylinders, exactly. Okay. Now, this earliest engine for the earliest car, a modification of a motorcycle engine, and why the Japanese chose to do this, I'm not sure, but I believe, if I'm not mistaken, I have to think about it a little bit, I believe was a 100, and the Roman numeral for 100 is C, okay? 100 and 4 cc's. Anyone know what car that was? The Honda Civic. That's, I've heard, where it got its name, because it was 104 cc. Cc meaning cubic centimeters. That's an awfully small displacement engine, but that had been in the motorcycle, okay? They grew from there, obviously. But I've heard that's where they got the name Civic, okay? I don't know if that's true, but that's the rumor, okay? So anyway, just a little bit of trivia there. All right, so here is a table listing those SI base units. These are the 7 we saw 2 slides ago. They go back to this. The length unit is the meter. This is SI now, okay, the meter. And the symbol for it is just M for meter. Now, symbol, okay, that's the symbol for the unit meter. Whenever you see that, you've got to have a number in front of it. 10 meters, 17 meters, 3.4 meters, whatever, okay? That always is preceded by a number. Later, we will have parameters that stand for the quantity being measured. Those don't have numbers with them, okay? So, for instance, length, we might use the capital letter L for length, or we might use Y for length, or H for length, or something like that. But the unit is the meter, okay? Mass in the SI unit is kilogram. That's the only one that has a metric prefix on it, okay? Kilogram, because a gram was just too tiny. That's that little cubic centimeter of water, which is very, very, very small. Time is second, and that's the one that, for bigger units, we don't usually use kiloseconds or anything like that. We use the smaller ones like milliseconds, microseconds, and things like that. Okay, electric current was the ampere. Now that one's capitalized, these others were not. Does anyone know why? Why are some of the units capitalized and some of them not? Notice any trend, pattern? I snuck it in earlier, you may not have noticed. This was named after Louise Ampere. It was named after somebody. Those named after somebody are given capital letters. Kelvin, there wasn't a guy named Kelvin, okay? There was a guy named William Thompson. Well, where did they get Kelvin from? He was a British royal person. He was a lord. Lord Kelvin was his title, so they named it after him. And because the title was capitalized, so was the unit Kelvin. Okay? Other units for temperature. Does anyone know two other temperature units? Fahrenheit and Celsius, both named after people. Gabriel Fahrenheit was a German researcher. He came up with the Fahrenheit scale, and Anders Celsius was, I think, Swedish. He came up with the Celsius scale. Those are all capitalized. Lord Kelvin came up with the Kelvin scale. It's related to the Celsius scale, but we'll do that in chapter 4. Amount of a substance in a chemical sense is a mole, and that doesn't have, okay, they already use little m for meter, so they use 3 letters, MOL. Why don't they put the E on that? I don't know, but MOL stands for mole. And luminous intensity is candela, that's CD, okay? They probably avoided just C because C is centi as in centimeter, so they put CD for candela, okay? It's one very seldom used unless you specialize in that way. Say again?
Simplicity. Would that be measured in candles? Candela?
Candela, luminous intensity.
Would that be like 1 candle, 2 candles, or something?
That's where the name comes from, but it is a very specific measurement. We're not going to deal with it. I've never dealt with it in my career, but yeah, a candela is a very specific unit. Yeah, but it comes from the same source as candles. You're absolutely right. So how about the metric prefixes? Okay, we have smaller prefixes and we have larger prefixes. Let's go small to begin with. Let's imagine this is a meter. That's nowhere close to a meter, but let's just imagine. Let's split that meter into 10 equal pieces. What do we call the 1/10 of a meter? A decimeter, a decimal, 1/10. You know, it's all based on 10 fingers, 10 toes. You know, on our counting system, a decimeter. So 1 decimeter or 1 meter is 10 decimeters because there's 10 of those smaller divisions. Take that decimeter. Now this is a lot bigger than a decimeter, and split that into 10 equal pieces, and there you have 100th of a meter. 100th of a meter. What's 100th of a dollar, by the way? A cent, right? A penny, a cent. So 100th of a meter is a centimeter, and that's where you get the title. A cent is a centidollar. Okay, shortened to just be a cent. 100. How many years in, what do we call 100 years? A century, okay? You use that for 100. 100 centimeters makes 1 meter. 10 centimeters makes 1 decimeter. You take a centimeter, by the way, a centimeter is about, like I said, the distance across your little fingernail, so that's actually not too far off from being a centimeter. It's a little too small, perhaps. Take a centimeter and blow it up and divide that into 10 equal pieces, and then you have a millimeter. Okay? Now, these going down and up, the first 3, these are the only ones that we go by 1 power of 10. 10, 10, and 10. After that, we always go by 3s. Okay? You don't do a special name. So, starting with meter, then you have decimeter, centimeter, and millimeter. If you went up, does anyone know what 10 meters would be called? What are 10 years called? A decade. So that would be decameter. Okay, well, a decameter, decimeter sounds so similar to each other. This, by the way, is DM. This is CM. This is MM. So a decameter, they have to put another letter in there. I think they usually use either DK or DC. I've seen them both. I think it's DK. Okay, it'll show up in the book in a minute. Okay, now 10 decameters. Anyone know what that would be? A hectometer. That would be 100 meters would be a hectometer. So I think of 100 hecto. Now the only place that is used in a practical sense that I know of is if you were to buy a farm here in Alabama, what would you buy? What would be the units that you measure your land in? Acres. Okay? Now in the metric unit, the thing that would make the most sense would be a square meter would be way too small. So you do a square kilometer. A square kilometer is huge. Way, way bigger than an acre. Way, way bigger. But a square hectometer would be closer to being what an acre is. So a hectometer squared, they abbreviate or shorten to call it a hectare. Have you ever heard of that? You folks that are in the metric countries, hectare.
I've heard of it.
You have heard of it, yeah. That's what they measure land when they're selling and stuff. That's the only place I know of using hectare, okay, or a hectometer, okay, is a hectare. And that's a square hectare, and that's where the air comes from. But then 1,000 or 10 hectometers would then be a kilometer, okay. And after that, you go by powers of 3. So only within the basic unit, you go by 1 power of 10. After that, you go by powers of 1,000. Okay. Now, what are the advantages of these? Well, if you were talking about 1,000 meters, then you'd have to write 1,000 meters. Okay. If you wanted to shorten that, it's 1 kilometer. So you can make your numbers a lot smaller. So for large numbers or small numbers. If you're talking about a millimeter, that would be 0.001 meter. I'd get tired of writing all those 0.00s and you get lost if it gets too many. So you just give it a name, 1 millimeter. You know, that stands for 1,000 for everything. And it's not just meters. If you talk about grams, you talk about a milligram, a centigram, a decigram, a gram, a decagram, a hectogram, or a kilogram. Mostly we just use those powers of 3. They get bigger than that and smaller too, by powers of 3. If you talk about a liter, you talk about a milliliter, you talk about a kiloliter, okay, or a liter. If you're talking about a newton, you can talk about a millinewton or a kilonewton. They don't usually use that, but you could. So anything metric, an amp, you talk about milliamps, microamps, okay, right? Or megaamps, or megavolts, or megawatts, okay? You use the same metric prefixes for whatever, and they always mean the same number. So the metric system is so regular. English system, give it up, okay? Nothing's regular there. 1,760, 16, 12, height, you don't have any idea what's next. So, what do we understand from measurements anyway? Well, data. Information. Okay? That's what, anything you measure, you're receiving and dealing with data. Now, by the way, and you hear this misdone all the time, if you ever hear someone on the television or radio or anywhere else say, this data shows, wrong. Data is always plural. A single piece of information is called a datum, D-A-T-U-M. It's a Greek word. Plural is data. So it should always be these data are. These data show, not this data shows. That says it's singular. It's not. It's always plural. Okay, so you get the basic data. And then what we do from that, we start looking at relationships. Okay? I've already mentioned some of these. We measure length and we measure time. And we combine length and time by length divided by time, and what does that give us? Miles per hour. Feet per second. Kilometers per hour. What does that give us? Speed or velocity. Exactly. Okay? So we start doing ratios. We divide one thing from another. If you have a change of velocity per unit time, that gives us acceleration. Meters per second. Miles per hour per second. Okay? We use ratios. Miles per gallon. Okay? Just all sorts of ratios we use. Pressure is pounds per square inch. PSI, pounds per square inch. Use your ratios. You look at things, you look at data, and you compare it. You divide, okay? You generalize. We'll look at one particular ratio, the density ratio. And most of the time we talk about mass density, and that would be mass per unit volume. Kilograms per cubic meter. Pounds per cubic foot. That's a weight ratio, not a density of mass ratio. So that's mass density or weight density. Then we can expand to symbols and equations. Now the symbols is what I was talking about. We let stand for a quantity. Like mass is M. Well, the little m, when it's a unit, that's a meter. When you're in an equation or a formula, you see F equal MA. There's no numbers associated with that M. That is a symbol standing for mass. So sometimes these can get a little confusing, but just keep separate what your symbols are and what your units are. Your equations relate to the symbols. Now we'll do problem solving made easy. That sounds really likely right. Okay. So let's look at data first. Ways we can measure things. Okay. So measurement information is used to describe either the objects, the depth, the size, the weight, whatever, conditions. We might talk about the temperature outside, the barometric pressure. Those are all forms of data. Events, okay? That might be a speed, that might be an acceleration, that might be something like that. Changes, okay? What would be a typical thing that you would measure a change? Perhaps your gas mileage usage as you go from accelerating to cruise control. That would be, you would use data to investigate. So here's a real simple one, okay? Here's a cube. Now what makes a cube a cube? Anyone know? Two things have to be true for it to be a cube. Say again? All sides are the same length. Absolutely. Now this is drawn in perspective, so that's so each of these sides is, they're saying is length S. S here, S here, S here, S here, S here. All these lengths are S. Okay? The other thing?
6 times.
Second.
6 lengths.
6 lengths. Okay, what do you mean by that?
Cube has 6 lengths.
Okay. 1, 2, 3, 4, 5, 6. That's what you see. But you see there's another one back here, another one there, another one there that you don't see. So it's actually more than 6. But yeah, we'll get to that. Okay. There's 6 faces on the cube. Now that's true. Okay. Now we haven't gotten to that yet. Okay. So not only are the lengths equal, one other thing has to be equal for it to be a cube. The angles are all equal. They all have to be right angles. If you sat on that cube and skewed it, it would be another shape. It wouldn't be a cube anymore. Okay? Even though it still had equal lengths, you'd have to have equal angles, and they all have to be right angles. We're not messing with those right now. Okay? So let's say we have equal. Each of these sides is S, whatever S is. 1 inch, 1 centimeter, 1 meter, 17.3 meters, whatever it is. They're all the same. Now, how about this face right here? We measure the length in centimeters, inches, meters, yards, furlongs, whatever. Okay? What do we measure the face is? That's an area measurement. And how do we measure an area? A length times a width. Okay, but the lengths and widths are equal, so then the area is length times length, which is S times S, which we say is S squared. Okay? Now there is a reason they used S. I sort of wish they hadn't, because you think of that as a second. Well, a second is a unit. You always have to have a number with it. This is a parameter. Okay? So S is fine, and area is a parameter for area. So the area of a cube, this side would be what? Area? S squared. But then there's a back side, that's 2 of them. There's a top and the bottom, that's 2 more, and a side, right side and left side, and they all are S squared. So that's for 6 S squared. 6 times the area of one face, you have 6 faces, front, back, left, right, up and down, top and bottom. So you have 6 sides. So you have 6x squared is the area of the entire cube, the surface area of that cube. What's the volume of the cube? Length times width times height. Length times width, length times width times height. Okay? And that's S times S times S. That's just S cubed. Okay? So that's how we talk about these. One face is S squared, 6 faces, which is the area of the whole cube, 6S squared, and the volume of the cube is S cubed. Now, what we're going to do is look at some different ratios. Okay? And a ratio is an analysis through a quotient. That's supposed to be through, not though. Okay? Through a quotient of 2 numbers. So let's say we're considering the area to volume ratio of a cube. So let's start with a real simple cube, 1 inch on the side. Okay? So let's go back to this cube here. And let's say it's 1 inch on the side. So that's 1 inch by 1 inch by 1 inch. Okay? Now, what would be the area of one of those faces? One square inch. How many faces do you have? 6. So that would be 6 square inches. What would be the volume of that cube? 1 cubic inch. So for a 1 inch cube, the ratio of the area to the volume would be a 6-to-1 ratio. Right? 6-to-1 ratio. And that's what we've got here. The area is 6 square inches. The volume is 1 cubic inch. So the area to the volume ratio. Now, I take a little bit of exception here because I really think they should keep the units in it. But that gets a little confusing, so they ignore the units. This number by itself means almost nothing. But this is 6 square inches per cubic inch. You really should have the units in there too. But that just makes it a little confusing. Okay? Let's expand and go back, and let's say this cube is 2 inches on each side. So what would be the area of one face here? 4. 2 inches by 2 inches is 4 square inches. And how many sides do you have? 6. 6 times 4 is 24. So the whole area of that cube would be 24 square inches. What would be the volume of that cube? 2 by 2 by 2 is 8 cubic inches. So 24 square inches to 8 cubic inches, that's a 24 to 8, that's 3. The area to volume ratio is now smaller, even though the cube is bigger. The area to volume ratio is smaller. Well, let's go up again. Whoops, wrong way. Let's make this 3 on the side. 3 inches on this side, 3 inches that way, 3 inches that way. What's the area of this face? 9 square inches. How many sides do you have? 6 times 9 is
54.
54? Okay, double that? Okay.
I'll check down.
No, that's all right, I know. Getting late, folks. I understand.
Three,
Okay. So 50, I'm going back up, bumping that. Okay. 6 times 9 is 54 square inches is the total area of that. What's the volume of that 3-inch cube? 3 is 27. And the ratio of, there's your 27. The ratio of 54 to 27, that's now to a 2 area to volume ratio. Okay, yeah.
So how that the last is measured?
How is what?
How the last column is measured?
How are these measured?
Yeah.
That's why I said they should list units, square inches per cubic inch, square inches per cubic inch. Because that's what you're doing. You're taking area and square inches dividing by cubic inches. Or you could say per inch per inch per inch, which is correct, but it's rather it's square inches per cubic inch, square inches per cubic inch, square inches per cubic inch. So what that's saying, the bigger the cube, the smaller the area of the volume ratio. Okay? And that does sort of make sense as you go. Now, think about it the other way. The smaller you go, the larger your ratio is. Area to volume. Now, let's think on a couple things. Who has a glass? No one has a glass of anything. Oh, yeah, you do. What did you have in your glass? Second? Okay, well, was that all that was in there? Ice, okay. Now, how was the ice? Huh?
It's melted.
Yeah, I know, but how, when you first had it, how was it?
Cold.
Okay, I'm thinking fine.
Small.
Oh, it's small, it was crushed ice, right? Very small chips of ice. Okay, it wasn't cubes, wasn't big cubes of ice. Now, which would cool your drink faster? Crushed ice or cubed ice? Crushed ice. Why? Because the smaller the size of the ice, the larger your area to volume ratio was. The more surface area you had to cool your drink with. So that's what an advantage of this is. The other, I don't know if any of you have ever done it. If you had to peel 5 pounds of potatoes, would you rather have large potatoes or small potatoes?
large potatoes.
Second?
Large.
Large potatoes. Because 5 pounds of large potatoes is a lot fewer potatoes with a lot less surface area, less peeling to do. If they're all small potatoes, your area to volume ratio increases like crazy. I'd rather peel large potatoes than small. Not 6, of each. I'm talking about 5 pounds each. Okay? So here's what we get with a small cube. Your area is here, your volume is very small, your area volume ratio is there. A larger cube, 2-inch cube, that's this one, your area, volume is increased, your area to volume ratio has gone down, and then for your largest cube, your area is quite big, but your volume is shot up quite big, your area to volume ratio is even smaller. So that relates these. So you see, your ratios can generalize a lot of things you might not think would go in the same direction that they go. All right, now here's a ratio that we're going to deal with a little bit. Now, sometimes I get carried away and forget to look at the book, okay? Let's just make sure I haven't missed anything that's really important, okay? They did show some of the body part things that we were talking about, and I mentioned just about all of them except one. What do we call the distance from fingertip to fingertip? That's a fathom. For any of you who are thinking of going to sea ever, you measure depth in fathoms. Okay? Now, just a little piece of trivia here. Your distance from fingertip to fingertip is approximately your height. Okay? Have someone measure it sometime and see. Now, it's not always. Some people with extraordinarily long arms are going to be, maybe not quite as tall as that is, but most of the time it's very, very close. Okay? They also have some comparisons here. They're talking about the distance, let's see, between two cities here. Oh, these are hypothetical towns. Let's say they're 150 miles apart. Okay? We understand that. In fact, that's pretty close to Birmingham to Atlanta, isn't it? That's pretty close to 150 miles, right? That would be 50 leagues. A league happens to be 3 miles to a league. Where that comes from, I'm not sure. The only thing I ever heard measured in leagues was Jules Verne's novel on 20,000 Leagues or beneath the sea. Okay. Yeah. Okay. Second. 3 leagues to a mile. No, 3 miles to a league. 3 miles to a league. Yeah. What's that?
20,000 leagues.
Yeah. But that was how far they traveled under the sea in his submarine, Captain Nemo. Yes. But not down, around. Yeah. Well, all underneath. Yeah. Okay. Does anyone know what a nautical mile is? Okay. If you remember the weird measurement that a mile was, 1,760 yards, which is 5,280 feet. What weird numbers. So for nautical miles, they sort of rounded up. 2,000 yards, 6,000 feet. So a nautical mile was a little bit longer than a statute mile or a land mile. So 150 miles between Atlanta and Birmingham, that would be 130 nautical miles approximately. Now, for some reason, the Romans had a different mile, and that was 158 Roman miles. And the Romans were the earliest that really did a lot with great road systems. Yeah. And they had mile markers on their roads. Okay? And if you've ever heard the phrase, walk an extra mile, I don't want to get into too much that might offend someone, but the early Christians that were very much a minority, one way that they got their message out, the Roman soldiers were were allowed by law to make any person carry their armament for 1 mile. And all the roads had mile markers, so they to force anybody to carry their shields, their equipment and everything 1 mile. And that was legal. You couldn't make them carry it more than 1 mile. So between 2 mile markers, they could carry it, and that way the Roman soldiers could rest, and then they'd have to pick it up and carry it again. Well, the early Christians were told to, if you were ever required to carry it 1 mile, take it an extra mile. And why? So when they say, why are you doing this? Then you can tell them about your faith, Christianity. And that's why the Roman legions became the earliest converts to Christianity. This is really bizarre, but that was part of the story there. And so rather weird, but mostly true, I think. So the Roman miles were just about the same as ours, but not the same. A furlong, okay? A furlong is 12,000 furlongs is 150 miles. Where they get that, I'm not sure. What do they measure in furlongs, by the way? Horse races, yes. The Piedmont, and the Belmont Stakes, and what's the other one? The Kentucky Derby is it Preakness in the Belmont Stakes. They're all different number of furlongs. Okay. In surveying, a chain is 10 chains make a furlong. Okay. So a tenth of a furlong is a chain, and you use that in surveying. And they also use rods. 4 rods make a chain. Okay, so 48,000 rods. Cubits, then are, your first joint of your arm, fingertip to first joint, and then feet would be that. So anyway, not very useful, but somewhat interesting. Okay, just wanted to catch up to where we were. Now there's one other thing that didn't show up on the slide set, and I wish it did. And since most of you don't have your books, I'm going to show it to you. This, by the way, is a cube, and this cube is 10 centimeters on the side. So each of those little units there is a centimeter, so that makes 1 decimeter on the side, because 10 centimeters makes 1 decimeter. So that cube, that's 10 centimeters on the side, and by the way, a centimeter, 2.54 centimeters is an inch, okay? So centimeter is between a half and a quarter of a third of an inch, okay? So that's what we're dealing with there, okay? Now, if you got 10 centimeters by 10 centimeters by 10 centimeters, how many cubic centimeters are in that cube right there? 10 by 10 by 10. 1,000. So that's 1,000 cubic centimeters. That 1,000 cubic centimeters is exactly the same as 1 liter. Whereas in the old times when they talked about the displacement of a car from the Japanese cars and the cars that were from overseas, they talked about so many cubic centimeters. Today they talk about liters, right? Don't they say 1.4 liters or something like that? That's just taking a bigger unit than a cubic centimeter, a bigger unit by a factor of 3. Okay, and that way it doesn't seem like they're major engines that much bigger than they have. So a cubic centimeter is precisely the same as a milliliter. Now, in the old days, my mom was a nurse, and she always talked about giving medications in cc's, cubic centimeters. Nowadays, when they do dosages, they do it in milliliters. Exactly the same amount. It's just a different unit. Okay? So if you're giving kids sometime in your future, dosage you usually be given them in in milliliters nowadays. Okay. I think that has us up to where the slideshow is. Now we're at density ratio. The density ratio is a ratio, and by the way, what does ratio mean? Comparison of 2 entities in a division sense. Something divided by something. Miles per hour, miles per gallon, cubic feet per minute, where you measure airflow, or volume flow, liquid flow. So a ratio, this is a ratio of mass to volume. Now, what makes the density ratio a pretty important one? What if you had 5 pounds of copper here? That's going to take up a certain volume, right? What if you had 3 ounces of copper? There's not really much way to measure and compare those unless you took the mass of copper to the density, to the volume of copper, and did that ratio, and then no matter how big or how small you had, the ratio is always the same. It's an intrinsic property independent of the quantity. So if you know the ratio, the density of an object, you know basically what kind of object that is, without a doubt, no matter if it's a large amount or small amount. Now, one of the guys who first used that, and this is, I don't know if this is a true story, but it's basically been told so many times, everyone assumes it is. The guy named Archimedes, ever heard of him? Okay, he was Greek, and I'm trying to remember the name of the country that he was in. It wasn't Crete, I don't think. It was some kingdom, and his king really loved Archimedes, because Archimedes was a scientist, he was an engineer, he was one sharp dude, okay? And he came up with all sorts of things. This was a very small kingdom, and it was approachable by sea. And of course, back then, all the boats and ships were made out of wood. And it was a small kingdom, always trying to be captured or fought against by bigger kingdoms. So what Archimedes did, he set up lenses on the top of the mountain, the peaks, and aimed them toward the ship at the place where the sun came through, and he was able to focus the light on them and start the ships from burning. And he destroyed some fleets by doing that, saved the king. The king loved Archimedes. He was quite a character. I think he was the first one to come up with the idea of a catapult, okay, and use that as a weapon against invading armies or navies. He was one sharp dude, okay? Well, this king in this little kingdom had been given this really magnificent-looking crown by this other king that he didn't trust any further than he could throw it. But it's a beautiful, beautiful crown, and it looked like it was pure gold. It was gold everywhere that you could see. But he was convinced this other king was a cheapskate, and that he cheated him and probably put gold over some cheaper metal, and then said it was a golden crown. And he said to Archimedes, hey, can you figure out for me whether this is real gold or if it's a fake? Archimedes said, sure. He pulled out his pocket knife or something like a pocket knife and was going, he said, oh, no. If it's pure gold, I don't want it marred in any way. So you can't cut it. You can't unlock it any other way. How are you going to do it? Well, because gold has a known density. And by the way, it's hard to measure a crown because of all those intricate carvings and stuff, but he can measure the weight of the crown, and then how is he going to get the volume of the crown? He was puzzling on that until he went in, and back then they had the common, nowadays we call them Roman baths, that people go in. There was one area that everybody bathed in. So he went and to the public baths, and when he got down into water, of course he saw the water level rise. He went, Eureka. And Eureka is the word that I got it. Okay? And supposedly he went running from the public baths to tell the king he was so excited he had figured out a way to do this, because if you lowered the crown into the tub of water and measured the amount of water that spilled out, he could know exactly the volume of the crown, and he already knew the mass, and he could calculate the density, and that was the intrinsic property of gold. If it was less than that of gold, it was fake. It was fake. Well, so the story went, he forgot to put on his clothes, and went running through the streets naked saying Eureka. Now, whether that part's true or not, I don't know. But he was a scientist, so anything is possible there. Okay. So, it's a characteristic of a given material. Now, since we in the U.S. system, U.S. customary system, the English system, we don't use mass. Who measures anything in slugs? We don't. We use pounds. Then we do weight per unit volume or pound per cubic feet. We'll use that density. But, you have to be near the surface of the earth, which always we are, to use that. But really the best one is the mass per unit density. Okay? So it's a ratio. Now the symbol, and I don't know why, but they use the Greek symbol rho. That looks like a P, but it's really like our letter R. That's a rho. That's a density measurement. Rho is equal to mass per unit volume. Now, again, these are not units. These are parameters. Density, the parameter for it is the Greek letter rho. Mass, the parameter for it is the letter M. That has nothing to do with a meter. A meter is a unit. It uses this as a symbol for the unit, but that one always has to have a number in front of it. This one does not. And volume, capital V, is volume. Now, why might we not use little v for volume? Why did they put capital V there?
Velocity.
Say again?
Velocity.
Velocity, absolutely. Velocity is measured, the the parameter for velocity is little v. Parameter for volume is capital V. Absolutely. Okay. Now, this is just illustrating what they're saying here. Gold, no matter how big or small a quantity of gold you have, hopefully you have a lot, but it's 19.3 grams per cubic centimeter. If that's a centimeter, 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 that's a cubic centimeter, that gold would have a mass of 19.3 grams. The same size cube of iron would only have 7.9 grams because the density of iron is much less than the density of gold. The density of water, by the way, remember how we said it? That's how they defined what a gram was a cubic centimeter of water. So that's exactly 1.0 grams, okay? And air, by the way, is 1 cubic centimeter. That would be 0.0013 grams on average, okay? So the greater the density, the more mass you have in the same body.
How do you measure air?
Very, very carefully. Okay. But air does have mass. I've seen this illustration of it. If you ever were to go and buy two identical balls, say footballs, soccer balls, volleyballs, anything that you blow up. Okay, two identical ones, huh?
Take the air out and weigh it.
Okay, yeah, but when you buy them, they're deflated, right? Put them on the scale, and you'll see they weigh the same thing. Fill one up with air, put them on the scale, and you'll see it weighs more than the. So air does have weight or mass.
I'm just curious.
Yeah, but that's one way to do it if you knew the exact value. Okay, but you have to be careful because you've got pressure then getting into it and stuff like that too. But yeah, where air does have weight or mass. Okay. Yeah, and by the way, another way you know it does. Is there any weight on you right now? Any pressure on you? Yeah. 1 atmosphere of pressure. You know how much that is? 14.7 pounds per square inch. Now remember what a square inch is? A square inch is about your 2 thumb joints left back. And just think about how many square inches there are on your body. Multiply that by about 15. That's how many pounds of weight are on your body right now of air, of atmosphere. Why don't we feel it? Because we're used to it. We have more than that pressure coming out of our body. Because if you ever nick yourself and bleed, blood comes out, it doesn't go sucking in. Okay? So yeah, you have more pressure inside your body than there is out of your body. Now, my mom used to do this, and now I can do it a little bit. She used to take the skin of her hand and do it up like this. It would stand there for several seconds. Mine goes down slowly. You young people, yours goes immediately back. Yours doesn't stand up there at all. Because my internal pressure is not as strong as it used to be as yours is now. Because the old valves are leaking. Okay. Now, before we get to symbols and equations, I think that's the next one. Yeah. I wish they had this table. They don't. But I'm going to put it up here. I know you can't read it from where you are, but when you do get your book, this is where it is. Here are some common densities. And again, if you know the material, you can look up its density. If you calculate the density, you can almost tell what material it is. Aluminum, 2.7 grams per cubic centimeter. Okay? Copper, 8.96, almost 9 grams per cubic centimeter. Much denser than aluminum. Iron is actually less dense than copper, 7.87. That's this one right here, 7.9. Lead, way dense, 11.4, but still not as dense as gold. Okay? Water is exactly 1.000, as many zeros as you want to put, grams per cubic centimeter. Seawater, however, is a little denser than plain water. Why? Because it has salt dissolved in it. And salt is heavier than water. So that gives it a little more density, so that's 1.03. Now, going back to Archimedes, I guess all of you have swum in a swimming pool before, right? Okay, and in a swimming pool, at least when I was younger, I was a sinker. Okay, I wasn't a good swimmer either, but if I ever got in the pool, I was going to sink, okay? I had to really always be doing, I couldn't float. But in salt water, I do float. Just barely, but now I probably do better than I did. But I was, my wife would tell you I'm really dense. But anyway, in a different sense. Okay, never mind. Okay, but so seawater is a little denser than fresh water, so therefore it's easier for you to float. Now they say Salt Lake City, the Great Salt Lake, it's really easy to float in that because that's even saltier than seawater. And if you really want to get to a place you float well, go to the Dead Sea. That is so concentrated with salts. They say it's almost hard to get underwater there, and I don't think you really want to either. But that's really, really high concentration. Mercury, however, is 13.6 grams per cubic centimeter. But what is strange about mercury? It is a metal. It's very dense. But what is it at normal temperatures and pressure? Only metal like it. It's a liquid. That's why it's in a thermometer. It's a liquid. It's 13.6 grams per cubic centimeter. What does that mean? That means if you had a ball of lead in a pool of mercury, it's going to float. Because it's less dense than mercury. Okay? Bizarre. Gasoline, 0.68 grams per cubic centimeter, which means gasoline floats on water. And you know that probably. Oil spills and things like that, always the oil is on top, water underneath. Now, in our old tractors that we had growing up, we always had, I guess it was under near the carburetor, the little cup that the gas went through. I know it had a name, I can't remember what it was. And if you ever got water in your gas, the bowl? Yeah. What kind of bowl? Float bowl, okay, yeah, because the thing above it floated. And if you got water in your gas, you could see it collecting there, and you better, you knew you better probably drain your gas tank, because tractors set out a lot and quite often get water leaked in somehow. Okay, so there is what they say about density. Now, here is where pencil and paper come in handy, because periodically in the book, they do have these examples. And let's see if we can do this one. Let me see if, here's a good place to do it. Example 1.1 on page 9. 2 blocks are on a table. Now, I don't draw very well, so just put up with me. Okay, let's say that's our table. And we have 2 blocks on the table. I don't draw very well at all. Okay, suppose that's on the table too. 2 blocks on the table. Okay? Block A has a volume of, the volume of block A is 30.0 cubic centimeters. Now, time out a moment here. Why would we say 30.0? What does that 0.0 mean to us? If it's 30, it's 30, isn't it? Why do you need a 0.0 there? What does that indicate? You're measuring that with a huge amount of precision. It's not to the nearest cubic centimeter, it's to the nearest tenth of a cubic centimeter. That's exactly 30. Okay? So it couldn't be 30.1 or 29.98. It's 30.0. Okay? So it's good to 3 decimal places. Now that will come into play in a minute. Okay? And it has a mass. So the mass of this block A is 81 grams. 81.0 grams. And again, that 0.0 means it's not just 81 grams. To the nearest tenth of a gram, it's 81 grams.
Oh,
Okay.
so you said 81.0 grams?
Yes, 81.0 grams. Okay? Now, block B over here, really ugly. It has a volume, and this is not to scale, obviously. Volume of block B is 50.0 cubic centimeters. Okay? And it has a mass, so the mass of block B is, this is block B, this is block A. Okay? The mass of B is 135 grams. Okay? Now, are those all to the same precision? This one doesn't have a decimal after it, does it? But what gives you precision is how many significant digits you have. 3, 3, 3, 3. That's what those point zeros do. They give you precision to 3 significant digits. That is the same precision, 3 significant digits. Okay? So, if the two blocks, okay, which block has the greater density? So that's what the question is. So what we're looking for is density. So let's do row of A. What you reckon row of A is? Say again?
Block A.
Yeah, row of block A. How do we define density? Mass per unit volume. There's the formula right over here, okay? So it's the mass of A divided by the volume of A. And what was the mass of A? 81.0 grams. And the volume of A was 30.0 cubic centimeters. Okay. Now this one's fairly easy to do because everything's divisible by 3. So let's just make that 3 will go into 8 2 times, and 3 will go into 21 7 times. But then you have an extra 0 because you got 3 digits of precision. So it's 2.70 grams per cubic centimeter. Okay, so that's the density of block A. Okay, let's do the density for block B. And what would that be? 135 grams divided by 50.0 cubic centimeters. Now I know 5 will go into both of those things, and how many times? 5 will go into 13, 2 with 3 left over. 5 will go into 35, 7.070. That's also grams per cubic centimeter. Okay? So guess what? Those are the same block. I mean, they're different blocks, but they're made out of the same material. You couldn't get that kind of closeness and density unless they were the same material. And if you had your table, and I know at least one of you has a book, maybe more, what material was that? 2.70 grams per cubic centimeter. Aluminum. Both of those are aluminum blocks. Maybe they're going to be used in an engine. No, never mind. Okay. All right. All right. Let's do example 1.2. All right, to erase this one? Everybody got it? Okay. A rock with a volume of, so here we just have a whole rock here. And this rock has a volume, the volume of the rock is 4.50 cubic centimeters. Okay? It has a mass, the mass of this rock is 15.0 grams. What is the density of the rock? What's the density of that rock? What would it be? Help me, help me. What's density? Say again? 15.0 grams divided by 4.50 cubic centimeters. Okay? Now again, 5 will go into this 5 times. Okay, we really need an extra 0 there. 5 will go into this 0.900 times. That doesn't really help us any. If anyone's got a calculator, 15 divided by 4.5, what do you get? Say again? 3.333. Stop at that. Your calculator goes on and on and on, right?
Sorry, excuse me. Is that supposed to be 0.900 or is it supposed to be?
Okay. Let's just ignore that. I was just going to see if it's going to be easier to do. We're just going to use the 4.5. So, yeah, I erased too much. 4.50. Okay.
Okay, 15 divided by 4.5.
Yeah.
Next one.
You got 3.33 grams per cubic centimeter. And here's the thing with significant digits, folks. Even though your calculator says 3.33333333 for something like 8 or 9 places, don't do it. Look at your significant digits here. 3, 3, stop that in the 3. So count all 3 places, look to the right, there's another 3. It's less than 5, so drop those. If it had been 3, 7, you round this up to 4. So that's what we call rounding. Okay, remember when we talk about rounding your grades, you round normally. You count the number of digits, 3 significant digits, 1, 2, 3. Look to the right, that was another 3. That's less than 5, so throw it away. If it was 5 or more, then increases by 1 and throw those away. Okay?
So that means, I'm sorry, so that means that we just multiply?
No, you divide.
Oh.
This is the division line.
So divide?
15 divided by 4.5, yeah. Now, you don't have to put your point zeros on your calculator. The calculator doesn't care significant digits. That's why it gives you so many of them. But you make the carrying on it, and you round it to 3 significant digits. All right. Now, occasionally in the books, you'll have silly little, well, not silly, things like this. Could you calculate the density of your textbook? Yeah, you could estimate it anyway. You could do the width of your textbook, the length of your textbook, the thickness of your textbook, and come up with a good approximation of the volume of the textbook, put it on a scale and determine its mass, and you would have mass per unit volume. Now, if you're doing mass, I would say that would be in grams, measure it in grams, okay? And the volume, you would then the length you would probably do in centimeters, so you get cubic centimeters, grams per cubic centimeter. Then you can compare that to something in the table. Of course, it won't be any of those materials in the table, but you can compare it to that. Now, the book also has some of these things called myths, mistakes, and misunderstandings. Sometimes these are pretty good. Sometimes I think they're pretty lame. But when you got the book, read it and go over that. All right, any questions on density? Now, here's one thing I want to point out to you. Anytime you have a relationship like this, and so many of our things will be in these ratios like this. Now, this isn't the physics in me talking. This is more practically when I went to Navy schools, which were not always known to be that great, but they had these little devices they had to help sailors remember their things. Of course, I had been through college and knew most of the stuff anyway, so I didn't need these devices, but I do find students who found them helpful to you. I'll show them in a minute, but I'm going to show you 2 ways to do this. Okay, we know the definition is rho is equal to, density is equal to mass per unit volume, right? We can express that same relationship 2 other ways. And here's how we do it. First, let's multiply both sides of this by the volume, right? Here the volumes go out, and now you have mass is equal to density times volume. And if you think about that, that makes perfect sense. Let's take remember the copper we had? We had a density of 2.70 grams per cubic centimeter. Remember, that was the density of aluminum. Multiply that by a volume, any volume. Let's say 3.00 cubic centimeters. That's a good volume, right? Well, look at here. The units go away, and you're left with that would be 8.10 grams. That would be your mass in grams. So your units are your friends. Keep up with your units. Mass is measured in grams. That makes perfect sense. So that
excuse me, I'm sorry. So those two are the two ways of doing it?
Okay, yeah. Okay. You can. I'll show you another one in a minute. Density is mass per unit volume. Mass is density times volume. Okay? Now, here's another way. Let's erase all this. This is just illustration. Okay? Here's another way. Here we had density. There we had mass. How could we get volume by itself? Well, let's divide both sides by density. Densities go out here, and now you have volume is equal to mass divided by density. And if you think about the units, this would be in grams. This would be in grams per cubic centimeters. The grams cancel out, and 1 over cubic centimeter would be cubic centimeters. And sure enough, that's a good unit for volume. Okay? So this one formula here can be expressed in 3 different ways. Density is mass per unit volume. Mass is density times volume. Volume is mass divided by density. Okay. Now, I do not think this is worth memorizing, these 3 ways. Okay. What is good is keeping up with units. But here's the Navy way of doing it. Okay. I don't know if you'll find this helpful or not, but here is what I learned in the Navy, and I noticed other people have done it too. And you can do it either one of 2 ways. It depends on whether you like triangles or circles. I don't care. Okay? But what you do, you have a horizontal line, which is a dividing line, and a vertical line, which is a multiplication line. Okay? Now, when you have a formula that's like this, what's on top here is mass, so put your mass on top, right? And then put your other 2 variables down here, density and volume. Density and volume, okay? Now let's say you're looking for density. That gives you mass per unit volume. There it is. If you're looking for mass, that's density times volume. Remember we had that one. If you're looking for volume, that's mass divided by density. Okay? And this will work every time you have a relationship that is either a ratio form or a multiplication form. For instance, distance is equal to velocity times time, right? If you're traveling 60 miles per hour, you drive for 3 hours, you go 180 miles, right? So you know that distance is equal to velocity times time. Well, there's velocity times time. Put them down here, put your distance up here. And then you have velocity is distance divided by time. Time is distance divided by velocity, and distance is equal to that. Yeah, they all work. Anytime you have 3 entities related by either multiplication or division, set them up in your either triangle or circle. It doesn't matter. Now that's sort of the easy way. When y'all did Ohm's law, did you use something like this or not?
Exactly.
Huh?
Exactly.
Exactly. Yeah. Okay.
E on top and
IR on the bottom. And then when you're doing power on top, current times velocity on bottom. Anything that relates in a multiplication or a division sense, you can set up on these. Okay? I don't know if you find that helpful or not, but it's there.
I did.
Huh?
I did in the 60s.
Yeah, exactly.
They called it the Wilkie button. I don't know
What's that?
They call it a Wilkie button.
Wildy?
W-I-L-K-Y. I don't know
Oh,
why.
Wilkie. Maybe Wilkie came up with it. I don't know.
For
Oh.
somebody who was running for something.
Oh, I see. Got it. Yeah. Yeah, there was a guy who was running for something called Wilkie. I remember that. I don't remember what he was running
I
for.
don't know, but that's what they use.
Yeah. Wow, I hadn't heard
Still
that.
works today.
Yeah. So there's your ratios, and lots of ratios can use that. Fuel efficiency, miles per gallon. I mean, anything that you measure in division or other sets. Okay. So let's move on to symbols and equations. This is on page 10 in your text. Okay? Now, I was hinting at this earlier, okay? Symbols represent your quantities, the measured properties. Like mass, the symbol for mass is just about always little m. The symbol for volume is almost always capital V. The symbol for density is almost always rho. The symbol for length could be S, it could be H if it's height, it could be Y if it's height, I mean it could be X. They use lots of things for length. It could be L for length, okay? Weight is usually little w, work is usually capital W, okay? So you have symbols representing the various quantities. Force is almost always F, capital F. If you're talking about frictional force, it's almost always little f. I don't know why, but they do that. Okay, now equations are what we just had when we had the density equation. These are mathematical relationships between these properties, and you use the symbols in there. Now these can describe properties, they can define concepts, or they can specify relationships between them, okay? Like Ohm's law, like the power formula, and like any other thing like that. That's the advantage of symbols and equations. They represent the characteristics that are always true about these various things, okay? Just like density equation, density is mass per unit volume, and then you can manipulate that equation like I did the first time, which is how I learned to do it, and then using the symbols, the Wilkie buttons or the triangles, either one. I kind of like the triangles better because you have one number on top and two on the bottom, but they both work, and they work well, okay? Now, there's various ways that things are related to one another, and we'll talk about these next. And it kind of, I mean, it's kind of common sense, but it also is somewhat a bit more precise than just common sense is. Okay, everybody got it? Okay. And they entitle it More Math, okay? I don't know why. Certain things are related to each other in what they call directly proportional, okay? For instance, if I'm driving at a constant speed, the time that I drive is directly proportional to how far I've driven, right? If you're going at a constant speed, the longer you drive, the further you go, right? That's a direct proportionality, okay? Whereas, if I was traveling from here to Tuscaloosa, say, and I went at, that's a constant distance. But if I go at a faster speed, my time is going to go down. If I go at a slower speed, the time's going to increase. That's an inverse proportionality. Directly proportional, they go up together or go down together. Inverse proportionality, they go at the other. It's an inverse proportionality. If one goes up, the other goes down. Okay? That's an inverse proportionality. Think about this. Think of a fraction. Okay? A fraction, let's keep the numerator to be a 1. Let's change the denominator. So give me a small denominator. 2. That'll give you 1/2. Give me a bigger denominator. 3. That's 1/3. Now, which is bigger, 1/2 or 1/3? your bigger denominator gives you a smaller fraction. That's an inverse proportionality. Okay? Now, we have what we call proportionality constants. Okay? Now, and we also have, this slide is put together rather strangely. We're going to come back and show you what these are, and then I'll come back and tell you what they're talking about there. Okay? So, hold up. Here's what we're looking for. A direct proportionality is written this way. A is proportional to B. Okay? Now that symbol there looks a lot like the Greek letter alpha, but it's not an alpha. Okay? It's lowercase alpha. It also looks a lot like a goldfish. Okay? Those little goldfish you eat. That's what it reminds me of, I think, in terms of food. But what that symbol means is proportional to. A is proportional to B. This is a direct proportionality. That means if A increases, if B increases. A decreases, if B decreases. Okay? That means they go in the same direction. A is proportional to B. That's a direct proportionality. Okay? The inverse proportionality would be like this. A is proportional to 1 over B. So if B goes up, A goes down. If B goes down, A goes up. That's an inverse proportionality. A is proportional. You use the same symbol, but you put the second one in the denominator. And again, if the denominator gets bigger, that means this gets smaller. Okay, 1/3 less versus 1/2. Yeah. So it's going in the opposite direction. Now, what is the proportionality constant? The proportionality constant is the number that will make the proportionality into an equation. Okay? What? Okay. Let's go back to this one. Okay? Now, to make that proportionality into an equation, introduce a proportionality constant. A is equal to KB. That is proportionality constant. In other words, remember we said if B increases, A increases, by the same amount. That amount would be your proportionality constant. Okay? So you change this symbol to an equal symbol by introducing the proportionality constant. I can deal with equations a lot easier than I can deal with proportionality. That just shows the relationship. This is something that you can actually make. Okay? So the proportionality symbol is the same as equal K. Okay? Equal K is proportional to. And you can do the same thing with this one. Let me erase that. Oops. Not the one I wanted. Okay. Yeah. And this would become A is equal to K over B. Okay? Equal K is the same as proportional to. Okay? Equal K is the same as proportional to. Again, as A increases, B would have to decrease, or if B increases, A would have to decrease. They go in opposite directions.
K over B is inverse.
What's that? Yeah. A is equal to something K over B. That's an inverse proportionality. Exactly. So that's written as an equation. That's just written as a proportion. That symbol, the fish-looking symbol, is the.
And the one on the right is a direct
Yeah.
proportion.
Yeah. That's your direct proportionality. Yeah. Okay. Let's see what they do with it. Here they did. See, they get there so scattered. I would have kept this on the same thing. So see, this has changed that proportionality that you had up there into an equation. The proportionality is the same as equal K. Okay. Now, so these are called the proportionality constants. Let's see if they do the other one. No, they don't, but A is equal to 1 K over B. That would be the inverse proportionality. Now, they don't say anything about numerical constants. Now, the only thing I can figure here is this. Okay? You have some proportionalities, constants of proportionalities. When the two units you're comparing are the same units, then you just have a numerical constant. When they're different units, like I was giving, the distance you drive is directly proportional to the time you drive. If you're driving at constant speed, then that's a proportionality constant. But you see, you're talking about time on one hand and distance on the other hand. So your constant will not just be numerical, it will have units. And what that constant is the speed. Distance is equal to speed times time. The speed would be your, if it's driving at constant speed, that would be your proportionality constant. That speed is not just a numerical constant, it is a dimension constant. Miles per hour, 50 miles per hour, 70 miles per hour, whatever it happens to be. Whereas some ratios like that, some things, you're looking at the same units. Then your proportionality constant may just be numerical. And one that we're going to deal with in lab will be one of those numerical constants. I don't want to give away what we're going to be doing, but we will be using one that doesn't have units that will be just a numerical constant. Okay. Now, there's one other thing they mention in the book that they don't mention here. There's another kind of proportionality. If A is proportional to B squared, that means one is proportional to the square of the other. Okay? And that is called here's the one I was thinking of. A is proportional to 1 over B squared. I can't write. Okay. That's called an inverse square law. And you run into these in nature all the time. Okay? Inverse square laws. And here's an example of one. My wife likes to read at night. When she wakes up in the middle of the night, she can't go back to sleep, she likes to read. So she has this little clip thing she puts on her book or a Kindle or whatever that has a light that just focuses right there. And it makes it quite light enough to read. Okay? So I'll wake up sometime and see the light on and know she can't sleep. I'll roll over and go right back to sleep. So it doesn't bother me any. Aggravates her like crazy. But, you know, but anyway, could she take that light and hang it from the ceiling and read by it that way? No, because light falls off by an inverse square law. You double the distance from the light and your light intensity falls off by the square of the light. So, and the same thing happens in a lot of things that you may be familiar with. For instance, kinetic energy is 1/2 mv squared. You double the velocity you're driving, the energy goes up by 4 times. You triple the velocity you're driving, the energy goes up by 9 times. And energy is related by how much work it takes to stop. That means if you're following somebody at, say, 30 miles per hour, and you get, say, 50 feet from them, and that you find that a safe distance. If they're going at 60 miles per hour, and you still try to do 30 feet behind them, you ain't gonna stop. Because if they were to stop suddenly, you're no way you're going to stop there. Because the energy that it takes to stop, the force that it required, is the energy is a squared velocity. It is a squared relationship. And even if you double the distance from 30 feet to 60 feet, that's not going to be enough. If you're going at twice the speed, you have to 4 times the distance to stop. That's why tailgating is pretty hazardous, especially at really high speeds. And that's why things like the racetracks, if they ever have a wreck, they are pretty spectacular because we won't go into that. In your book, on page 11, you'll see why that inverse square law works. They have a really good illustration there. Okay. Now, in just about every math book, and perhaps most of your science books too, there's usually a section sometime near the beginning on how to solve problems. Okay? And they give them in steps, and not always are all the steps necessary to be followed strictly or in exactly the same order. Some of them can be rearranged. But let me give you my rendition on these. Okay? Now this is a little bit artificial in that we're dealing with problems they give you in the book. Whereas in the real world, your problems just sort of land in your lap and you have to figure out what they are. But still a good process to follow. Now they're giving as if it's just something given in the book. Read through the problem, and here's what they suggest, and it's not a bad idea. I kind of do it, but I don't do it the same way they do. As I read through the problem, remember when I drew the table and had the blocks on the table, ugly blocks, okay? I don't like to draw pictures, but I draw pictures because often pictures are worth thousands of words, okay? You can see what's going on better with a picture than you can just reading the text. Okay, but as I was writing, I also filled in. The volume of the block was this. The mass of the block was this. I wrote them down as I did. They say put them in a list. I don't think a list is necessary. Put them somewhere that makes sense with the drawing. Okay, so you know what you're talking about where. Okay, so then when you go to do density, you already got them together. And I subscripted. Block A, density sub A, mass of A, volume sub. So I know what to keep together. Okay, so use your symbols appropriately. Okay, so it says read through the problem and make a list of the variables with their symbols on the left side of the page. Who cares about the left side of the page? Okay, I like to draw the picture and put the symbols where the data wherever they do it. Now, again, I don't follow these steps directly, and I'll tell you when I don't. Inspect the list of variables and the unknown. Okay? Now, there is another issue. Okay? I'll kind of depart from this. When I'm reading the problem, I look for the question. Look for what you're looking for. Find that somewhere. It may be not a question, it may be find the density. Well, that's not a question, but there's what you're looking for, the density. Or what is the time? Or how long does it take? Or how far does he travel? You know what you're looking for. Write that down too. I usually put a question mark by that. So I'll have mass or volume or speed or whatever, and they give them these things, but when I get to the question, write that down too, and put the question mark there. I know that's what I'm looking for. Okay? What they say, inspect the list of variables and the unknown. Okay, they didn't say how to identify the unknown. Look for the question. Look for the thing you're looking for. Identify the equation that expresses the relationship between those variables. So you've got all the things down there. You've got the thing you're looking for. Find that equation that relates what you got to what you're looking for. Okay. Now sometimes you might have to manipulate what you got before you can get to the equation. Do it if it's necessary. Okay? Do whatever it takes. Okay? When you find that equation, write it. They say on the right side of the paper. I don't care where you do it on the paper. Okay? Then, if necessary, solve the equation for the variable in question. Now, that's what I was doing with the circles or the triangles. What you're looking for, cover it up and identify the equation that gives it to you. Okay? That's the easy way to do it. If you had it like we had originally, density is equal to mass per unit volume, and you're looking for volume, then you might have to solve this equation for the volume to get it mass per unit density. Okay? You can do it that way, or you can use the triangle or circle and do it that way. However it is, come up with the equation now. When they were saying make the list, That's fine to make a list. I write it sort of all over the page, as you can tell. Always put your units with the numbers. Remember, the numbers by itself really mean nothing unless you have a unit. Now, if you notice that this is in miles per hour and that in feet per second, you got a problem, Houston. You've got to convert the miles per hour to feet per second or vice versa. Okay? If you got miles per hour and centimeters per second, you got even a bigger problem to do. So you have to get that. You can't put anything in an equation if your units don't match up. Got to have the units matching. And I'll give you some examples at some point of how to do unit conversions, but we'll wait till we get there. Okay? It says now you're ready to substitute the number value in the units for the symbols. Okay? That's what we do. When you got it, plug them in, plug them in. And then do the mathematical operations as indicated. Now here, I think is an important question. Ask yourself if the number seems reasonable for the question that was asked. If you come up with a mass of something you know isn't very big, to be several thousand kilograms, you probably did something wrong. And what's more, make sure the unit matches what you're asking for. If you come up with, you're looking for mass, and you come up with a unit of meters, wrong answer. Because mass isn't measured in meters, okay? Or meters per kilometer. That's not going to work. I mean, you've got to have the answer matching what you have. And then I really don't care for their step 8. Draw a box around your answer. Now, I don't mind if you do that. It's a good idea, but that's not part of solving a problem in my mind, okay? Now, they give you some examples of that. Let's see if we can just do one quick example problem they give here. It says mercury is a liquid metal that has a mass density, we already saw this in the table, of 13.6 grams per cubic centimeter. Well, I'm going to write that down. The density, which is rho, of mercury, which happens to be Hg, you don't need to know that, but that's what mercury is 13.6 grams per cubic centimeter. Okay? That's what they gave us. The question is, what is the mass of 10 cubic centimeters of mercury? Okay? All right. Here's what they gave us. Here's the question with something else. Okay? We already know what this is. That's the density. What is this thing? What is that? No, it's 10 cubic centimeters. I don't mean that thing. What does this represent? 10 cubic centimeters. What do we measure in cubic centimeters? Second? Not density. Density is measured in grams per cubic centimeter. Second? Volume. That's what. So that is your volume. So identify what this is. The volume of the mercury. Okay? Now, do we have a formula that relates density, mass, and volume? Sure we do. That's density is equal to mass per unit volume. But we're looking for volume here. So either, and now folks, the book almost insists you do it one way. I say do it any way that makes sense to you. You can put the numbers in here and then solve for the unknown, which is volume. Mass. That's the unknown mass. Or you can solve this equation for mass and then plug in the numbers. I call it plug and chug or chug and plug. Either way you want to do it. Okay? Which do you like to do? Plug in the numbers first and solve, or solve for mass and then plug in the numbers? Second? Solve for mass. Okay, how do you do that? Isolate the mass. Multiply both sides by volume. And the volume goes out here, and you have mass is equal to the volume, which is 10.0 cubic centimeters, times your density, which is 13.6 grams per cubic centimeter. And look at that. Your units cancel out, giving you grams, which is exactly what you measure mass with. And what will that be? 136 grams. See, that's the units that's left. The mass is equal to that. Okay, you see how that works? Use your units. Your units are your friends. They help you know whether you're solving the problem right or not. Okay? Say again? I can't hear you.
What time is it?
It's almost time. Okay? In fact, it's close enough. So we'll start next time on the nature of science, and that will be, okay, listen up. What we'll do next time, we'll start with where we left off here. It won't take us our 2 hours and 30 minutes to finish this chapter. So we'll finish the chapter, then we'll get started in chapter 2, but at 2 hours left, we'll stop and do the lab for chapter 1. And then the next day, we pick up where we left off in chapter 2, and move on from there. And then the next day, we'll have the test on chapter 1. We don't ever have the test until we completely finish the chapter the next day. So take care. Good to see you. Looks like it's going to be a good term. Boy, I'm all worn out. What's